Okay. So thanks for joining on a Saturday. I know it can be tricky. We'll just get started in a couple of seconds. Okay. So people maybe who are viewing online, are they able to hear me? Okay. Okay, perfect. So let's begin. Thanks for joining. And so before today, I'm going to cover in great detail recurrent neural networks and transformers. These form like the backbone of architectures that are used for language modeling and majority of natural language processing tasks. But before I do that, I also wanted to share a little bit more about our department, what we do, what we stand for, and so on. So we are a very interdisciplinary department uh, where there is broadly two streams. One is computational science and other is computer and data systems. So like faculty colleagues and labs in the former apply computational methods to do, let's say, scientific research on mathematics, physics, chemistry, biology, and so on. Whereas computer and data systems involves research related to, let's say, databases, systems, computer vision, NLP, and so on. And we have a broad range of labs. So you can go here, look at all the people who are teaching and doing research here. Many of my faculty colleagues have had an excellent track record in doing high quality research and have a lot of students who are like really distinguished at this point of time. So you can check this out. I am sharing all these details to you because very soon, in about a week, there is an admission deadline that's coming up. So if people who want to enroll into IISc for, let's say, their PhD program or Masters by Research program or MTech by Research program, can check out this link, which is all about admissions. So this is the admission notice, and it gives you all the details about like who's eligible, how to apply, and so on. So there is a lot of detail here that you can go through if you're interested. But I'll share maybe a few key points. One is that if you are from a centrally funded technical institute, we have simplified the entry through that program. So let's say you have already gone to one of these 122 schools. So there is a huge list here. Okay, here I think. So there is a huge list here which includes, let's say, IITs, NITs, IIMs, IAS, ICERs, and so on. So we have a list of about 122 universities or institutes where you don't have to necessarily sit for GATE and qualify GATE. You are eligible to apply if you were a bachelor's or a master's in any of these institutes, so long as you hold a GPA of 8 and above. And another, I think, key point is that if you already have a master's, you are eligible to apply through the master's or MTech qualified mode of entry. So you don't have to again like write GATE or any other exam to be eligible to apply. So these are things that people I talk to often don't know. So I thought I'll just share it with you. Yeah, so the deadline for the same is about a week from now, 23rd March. And IISc offers, as you may know, like one of the best trainings in the country to do research, to build your career, to upskill, and alumni from our institute and particularly our department have gone on to become faculty members in other universities both in the US and India. Many of them are leading scientists at companies like DeepMind, Amazon, Adobe, and so forth. So I think this is a great opportunity if you are interested, and I'm happy to answer questions over the break if you want to know more about the program. Okay. So let's go to the content of the class. So last time we were very, let's see. Okay, so last time we were talking about neural networks and how they were initially biologically inspired. A neuron was like just something that took in a lot of signals, and based on the weight of all the signals it was activated, and we discussed how a perceptron was a computational model resembling the neuron. So if all the, like let's say these are the inputs, if the weighted combination of the inputs is greater than 0, then we say that this neuron is activated, otherwise no, the output is 0. So this is a perceptron. We looked at how a perceptron could model AND and OR functions or AND and OR gates, but we realized that it could not model XOR. Why? Because we realized that this boundary happens to be like a linear weighted sum, so it can only model linear functions, and XOR happens to be a non-linear decision boundary. Like you cannot draw a line here or here to separate this out, so which was a problem. But we realized that you could potentially club a few of these perceptron units to build a XOR. So as you might have studied in the past, like a combination of AND and OR gate can be used to model XOR. Similarly, a combination of two perceptrons whose outputs are inputs to the third perceptron can be used to model XOR. So this was left as an exercise for you to decide what are these weights, right? I hope you got a chance to think about it, but I think you probably got an intuitive sense that this is possible, you can do it. Okay, so we were able to model XOR through just 3 perceptrons. So we got inspired and thought, like, if this is good enough, just 3 are good enough, like why not, why not, okay, like why not scale this up? So we could potentially, instead of just having 3 perceptrons, we could potentially have multiple units or multiple perceptrons, and instead of having just 1 or 2 or 3 features, you could, let's say, have a large number of features. So here there are n0 plus 1 features. Oops. Right? All of them go into all the units. So there are, let's say, n1 plus n1 units, and this is a 2-layered feed forward network. So let's say this is just like a perceptron which accepts all these n0 plus 1 features and has a weight associated with them, and this weight, this like weighted sum of features determines the output of this. So this can also be, like, if you're comfortable with linear algebra, you could potentially also very simply write this as Wx. Instead of, like, this is, instead of just writing the equation for this, you are writing the equation for all of them in a matrix format. Any questions about this, like, or is this clear enough? So last time we also saw that the output was determined by this sort of thresholding function. If it is greater than 0, then we said 1. If it is less than equal to 0, we said 0. So this is this, like, kind of like a thresholding function where till 0 the output is 0, and above 0 the output is 1. But you can imagine to have more complex non-linearities, more sophisticated non-linearities. So we talked about a few of them last time. One was ReLU. One of them was ReLU. 1 second. Okay, one of them was ReLU, which looked a little bit like this instead. So it was 0 all the way less than equal to 0, and y equal to x for x greater than equal to 0. So you can imagine there could be multiple such non-linearities. The only reason why we need a non-linearity here is otherwise multiple layers can be just written down as a linear function. So if you apply linear operations on a linear function, like if you keep multiplying that with another w, another w, another w, you can club all of that and write it as one matrix. So this model will not be able to model anything except linear functions if there was not a non-linearity here. So non-linearity is somewhat crucial.
Sir, one question is like if that linear function of a linear becomes a linear, then in the case of the XOR, it was a non-linear decision function.
Yes, yes. So in the case of XOR, we were using a perceptron. So perceptron is also, like, if we look here, just because of this definition, it is like, so the decision boundary is linear, right? Because it's a weighted sum of these, but the outputs go through a non-linearity. Like it is this is the output function, right, essentially. So if this is your x-axis, right, and this is, let's say, your y-axis, so this output is, let's say, let me draw the outputs with black. So your outputs are 1 and 0, right? So this is also non-linearity, but a simple kind of non-linearity, if you want to call it that. Right, so now when you club these here in this function, you are applying non-linearities here. H1 and H2 can be like this is like the output of it goes through this thresholding function, right? Okay. So last time we also saw that one could potentially train these models using backward propagation or backprop. So let's say if you have something like a loss function here, right? What was the loss function, anybody? Yeah? Right. So loss function captures deviation from the expected output. There can be different forms of loss functions. One of them could be like, if you're predicting a real value, let's say, you could just say how far I am from that real value. Or you could have a mean squared error, or like you could, across examples, compute the squared distance from the expected value and take a mean. Similarly, there are lots of loss functions that you could use, but the idea is that loss captures how bad your model currently is. Initially, all the weights that I was talking about, all the W's will be random. So you will very likely misclassify a lot of examples, give gibberish outputs, and therefore incur a large loss, right? And now, so long as the loss is differentiable, we also discussed that you could apply a gradient based algorithm to slowly reduce your loss, right? So if loss is a function like this, right, so if loss is a function like this, and if you are here, you can take the tangent or the gradient here and slowly move downwards. This algorithm is called gradient descent. We talked about it a little bit in the past. So we also wrote down this equation. Right? This is just saying that I will update my W's in the negative direction of loss. So wherever my loss is decreasing, I will go there. Right? So this is also called the update step. But again, like all the libraries that you are anyway going to use in practice, like PyTorch, TensorFlow, JAX, they have what is called as an auto differentiation built in. So all these dl by dw will be computed for you. You don't have to analytically write it down. You don't have to do the math yourself. What it does is it actually applies this chain rule backwards. So slowly, like if you want to compute dl of dd, it will compute dl of de like this. Then it will compute de of dd, and then it will just multiply these two. This is like basic calculus. You might have gone through it at some point. It's called a chain rule. So if you want to compute a loss with respect to a variable, but there are multiple compositions or operations in the middle, this is how you back propagate your derivatives. You had a question? Yeah.
What happens in case the function is not differentiable?
Yeah. So ReLU is, by the way, differentiable except at the point 0 where it is sub-differentiable. So at point 0 you just use the value of 0 as its gradient. For ReLU that's not a concern, but in general if the function is non-differentiable then you cannot do gradient descent. So at least optimization through gradient descent is not possible, which is why for all neural networks we only use differentiable loss functions, differentiable operations. So it's a key requirement. Any more questions?
Sir, when the ReLU becomes 0, like output becomes 0, so we are like when the neural network, the weights are randomly initialized,
Yeah.
then are we perpetually stuck at that particular
Yeah.
0?
So great question. So so the question is like if you're using ReLU, a lot of times the values are 0. And if the values are 0, the gradient is also 0. So does that mean we are perpetually stuck there? So at least because of the way ReLU is defined, for those points you will not change if your loss is 0. So hopefully other weights are not at that state, which is why you randomly initialize, so not all values will actually be 0. So if let's say you initialize everything to 0 in your W's, you will end up in that situation. Another reason why you don't want to initialize everything to 0 is every single weight will have the same, there is no differentiation between weights, right? Every weight is acting the same way. You want different weights to start from different points so that they can potentially reach minimas, right? So again, like if you don't fully appreciate or understand this, that's totally fine. It's okay, because you can treat this as a black box where if your loss is differentiable, PyTorch and most other libraries allow you to just call this function loss.backward. It will compute all the gradients for you. Similarly, if you have any optimizer like gradient descent or Adam or whatever optimizer you are using, let's say gradient descent, all you have to do is call optimizer.step and it will take this step for you. So it will keep updating these W's and you can track how your loss is going down. Okay. So this is all we studied last time. This is a slightly more complex network of some variables connected to other variables. So let's say you have A and L. So L, if you want to write dl upon dA, so this is like you will compute dl upon dE, dE upon dd, dE upon dA, and then dl upon dE will be just dl upon dE upon dE upon dA, right? This is just chain rule. You can go home and maybe like really practice and think about this, but this is yeah, question. Yes. So basically the first step of backward, that's why it's called backward pass. So you start from the loss, you compute the function that's closest to the loss and compute the gradient with respect to that, and then one step back, another step back, another step back, and you multiply all those partial derivatives to compute the actual partial derivative that you need, dl upon dw. You can also maybe realize that if any of these are small, because of all the multiplication, some of these values can be very, very small. So this is also called as the vanishing gradients problem. You might have heard of it somewhere. Okay. So this is also called the vanishing gradients problem. This can happen if your neural networks are very, very deep. So that's why there is a big chain of multiplication, and one or two low values can really take your entire gradient to a very, very low value. And if your gradient itself is a very low value, then that means you are not updating much. Like if this is very, very low, either you need a bigger coefficient to multiply, or you will not change much. So either your step size needs to be very high, or you will not change much. Right, so this is like basics of deep learning, right? Okay. So we were looking at how you could potentially train a feed-forward network. So let's say if we were given a class, if we were given a task of doing text classification. What is text classification? Text classification is like just assigning some topics or some classes to a piece of text. So you might have seen this in many cases. Let's say you are reading a newspaper, or you are subscribed to some feed of the Hindu or the Indian Express. All of the news items get categorized into politics, sports, entertainment, and so on. Similarly, you might want to look at, let's say, product reviews, figure out how many of these are positive, how many are negative, and you want to, let's say, automatically categorize them. So, or let's say you have a company and people are discussing about this on Twitter, you want to just understand what is the sentiment of the audience or the users. So this is like very handy, useful problem, shows up at multiple places. So let's say here this is a review of let's say desert. It says desert was great, and you want to classify this as positive, negative, or neutral, right? So what you could do is you could, on textual input, use a neural network, but first this input should be converted to a set of real numbers to be able to feed into a neural network. So let's say you compute some features, or you extract some features from this piece of input text, right? Here let's say you have just 3 features. Feature number 1 says how much is your word count. Feature number 2 says how many positive words are there, and let's say you have a dictionary of positive words, great, awesome, amazing, fascinating, all that. So here great is 1, so your second feature is 1, and let's say this is a very simple pedagogical example, and the third feature is how many times you say no. No, it wasn't good, or no, I did not like it. So even though there are words like, good, presence of no is, let's say, important to capture. So if we just had a very simple network with very simple 3 features, we can take any input, convert these into 3 features, which are these 3 inputs, and they can then go into a neural network. So here let's say n is equal to 3, and it is going into dh number of units, like perceptron units, and outputs of all of those are further going into 3 units, and each of these units corresponds to 1 class. So one class will tell me how likely it is. So one neuron here will tell me how positive this is, one neuron will tell me how negative this is, and one neuron will tell me how neutral this is. Okay. Again, these will be raw real values to begin with. So this might be 9.1, this might be 8.4, this might be minus 10. You need to convert these into probabilities. We looked at a few things that you could use to convert these into probabilities last time. So one, like if you have just one value, so if you just have a scalar here, it is very simple to convert this into a probability. The very popular, commonly used function in deep learning to do that is sigmoid. You might have seen this somewhere. Sigmoid looks like this. So as you can see that as s tends to infinity, or as s becomes bigger, one second, as s becomes bigger, this value starts to become smaller and smaller and smaller. So this is 1 upon e to the power s, right? So as s becomes very large, 1 upon e is smaller than 1. this number almost vanishes. So this value goes to 1, right, which is also clear from this figure. Similarly, if s becomes negative infinity, then this becomes a very, very large positive value, e to the power plus infinity, and this whole denominator becomes very large, and 1 upon large denominator is close to 0. Right? Questions? Yeah.
Then if it's like if that probability after using sigmoid, you're getting like let's say this point 0.5, then it's like neutral. But if it's like 0, then it is not positive. So
Yeah.
why do you need 3? Like, is there any?
Yeah. So that's great question. So the question is, why do we need 3 outputs here? Can we just say we will make one prediction? If it is greater than 0.5, we'll call it positive, less than 0.5, we'll call it negative, equal to 0.5, we'll call it neutral. You could potentially do it, but you have almost killed the neutral class here, because it has to be either exactly 0.5 or very, very close to 0.5. Another example could be, let's say you want to classify your reviews into highly positive, positive, neutral, negative, highly negative. So either you will have to divide the probability ranges into some, like, okay, 0.6 to 0.8 is positive but not highly positive. So either you need to do that, or it's better to have independent classes. Similarly, if you were, let's say, identifying whether this is sports, news, politics, then 1 is not enough, right? You can't say 0.7 of sports is politics, right? So it's generally acceptable to have multiple output units corresponding to a output class. Okay. Any more questions? Yeah.
This is about the vanishing gradients problem you talked about. So the goal of the system is to minimize the error gradient, right? So why would it be a problem that it reaches a very low value?
Yeah. So that's a great question. Why will, like, ultimately you want low loss or zero loss? Why is like, your question is, why is vanishing gradients a problem, or why does it happen?
Why is it a problem?
Why is it a problem? It's a problem because your gradients are astonishingly small. So either you need a lot of steps to improve on that function, and so in practice you could take infinite steps with an infinitely small gradient and get to a zero loss. But in practice that just doesn't work, right? Because you don't have that much time. Also, there are underflow issues often, so computers might not be able to also handle very low values. So typically a lot of these calculations are done in log space just to avoid those underflows. Any more questions? Questions there? The person with the red shirt? So if you have questions, please feel free to ask. Yeah. Okay. Got it. So yeah, we looked at a sigmoid function which can take an arbitrary value, let's say 3.1, and it can give me a probability. Because this function is between 0 and 1, probabilities are also between 0 and 1. So this function can be used to model a probability distribution. So whatever you get out here, you will typically apply a sigmoid of that output, right? Here, S1, sigmoid of, let's say, S2, sigmoid of S3, which is why you will get a probability output rather than some number. So you will get a probability of neutral, probability of negative, and probability of positive, right? So that's one way to do it if you were to individually do this. Another way to do it, which is maybe better suited for multi-class problems, is what we call as a softmax. We looked at this also a little bit in the last class, where it is a normalization trick, where instead of just simply dividing by the sum, you exponentiate and divide by the exponentiated sum. So if you have a number like 162, you take an exponentiation of this and divide by the exponentiation of all the values. So e to the power 1 upon e to the power this is this value of 0.006. This converts a vector into a probability distribution. So as you can see, this sums to 1 by construction, by design. And this is also positive again by design. Exponentiations are never negative, so it's always positive, always between 0 and 1. And you can see that 6 here was the largest value. So the second index here is also the largest. So in some sense it is going to not change the maximum value. Like whatever was maximum in the first vector will also be the same index will be the maximum in the second transformed softmax output. So here a better thing would be to take out these 3 values and compute a softmax of this vector of 9.1, 8.4 and minus 10, and you will get 3 values each summing to 1, sorry not each summing to 1, in total summing to 1, each representing a probability corresponding to the first, second and third class, right. So you are able to take a sentence and do a task, you are able to take a sentence and do a task using a neural network, right. So we have kind of like made some progress here. You started with the sentence, you designed some features by hand, you wrote these things down, but after that you fed all these features to a neural network, you defined what is an error or what is a loss, and then the neural network did everything for you using backpropagation, right. Question, yeah. Yes. Yes, yes. So yeah, so I can maybe make this a bit more clear. Okay. So let's say if you were classifying something, you had a sentence, let's say desert was good, and you passed it through, let's say, a feed forward network, and now you got a probability distribution of, let's say, 0.1, 0.8, 0.1. But you realize that, so this is corresponding to the positive class, neutral class and let's say negative class. So you realize that this was supposed to be positive in my input, in my data set this is a positive example, but my model is saying that this is the output, this is, my model is saying it's neutral, sorry. My model is saying that this is the y hat, this is the predicted output as per the model, right. So the model is saying neutral, but actually it is positive. So you should incur some loss, a high loss potentially, right. So now your loss function comes in here to define what, like your loss function will dictate how big your loss is. So in classification problems or in K-class classification problems, one common form of loss is called cross entropy loss. I mean, forget the correlation or forget the connection with entropy, but the loss is very, very simple. It just says this is negative of log of probability assigned by the model to the correct class. So here it will be probability that the model assigns to the positive class, right. So here you will realize that the loss actually becomes P of y equal to positive, which happens to be very small value. So it will be P of 0.1. So if you remember your log curve, so this is something like this, right. So but the region of interest is just this, because probabilities are never going to be greater than 1. So here, like, here so here as close you get to 0, you will incur a high negative loss, but that high negative is countered by this negative, so you will have a very positive, like if I were to draw the negative of log, this will be the curve, right? So because the value is 0.1, very close to 0, this will incur a very high loss. Ideally, I want the model to take me very, very close to 1, so that I give this a very an exactly 0 loss. So just to recap this a bit, so you will typically apply loss which is negative log of likelihood that your model assigns to the correct output. So if it assigns a very high probability to the correct output, that means you are lying in this segment, that means you are lying in this segment, essentially, in this segment, right? So you are incurring a low loss. But if it assigns a low probability, then you are operating in this segment, essentially, which is high loss. So your question was whether the loss is applied after computing probabilities. Yes. Okay.
Sigmoid is one of the famous functions, right? And are there any function in with like second best, and why you use it?
So by default, most, like 99.99% of the networks will do multi-class classification problems, and the final loss is softmax. Like the final operation before computing the loss is softmax, which will give you probabilities. There are some interesting variations of softmax. One of them is called sparse max, which will by design give you sparse probabilities. It will say 1 or 0 only rarely. It will not give you like 0.8, 0.9, 0.1. It will either say 1 or it will say 0. So it will give you sparse output. You can read about sparse max if you're interested. But this is again like used in special cases when you need sparsity. But softmax is by all means like the default.
What would be the bound of this loss, like the loss functions? How is it only bounded between what would be the bound?
Right. What will be the bounds of the loss function? Great question. So at the lowest it can be 0. At the highest it can be plus infinity. Right?
When we are doing it between 0 and 1,
So the probabilities are between 0 and 1, which is why the negative log curve goes like this. So we are only interested in this segment of the curve because the input is a probability. So the domain of the input is 0 to 1.
so would it be meaningful if I say if my machine is having this much more loss, I do not have to, I should change the architecture in case.
Great question. So if my loss is high, should I change my architecture? Not necessary. You have to find a way to make your loss come down. So some architectures are more, let's say, compute effective or might offer different properties. So we'll look at some more architectures other than feed forward networks.
So this is like for the calculating of the loss while training, we are actually assigning the label that the output should be this class, and then according to that class, we will calculate only the probability of the output of that.
Yes.
Then what will happen if we have like multiple labels?
Multiple classes. Okay, great. So excellent question. So this is a setup where only one class is correct. sometimes you might have a multiple label output, like multiple choice questions with multiple correct answers. So this article could be both news and politics, but since it talks about Virat Kohli contesting elections, could even be sports, right? So there you need to change a little bit of this. There you need to make this into K binary class problems. So you need to, instead of saying pick one, you are going to say yes or no for first topic, yes or no for the second topic, yes or no for the third topic. So you should think of that as K binary classification problems. So for each topic you are deciding, is this correct or not correct. So similarly in that case you will apply a sigmoid for every class. So you will say that, okay, by 80% chance it is in news, 75% chance it is also politics. There you don't care about the probability summing up to 1 because multiple answers can be correct. In that case, yeah, okay, perfect. So how will the loss function look like in that case? So let me maybe add one more page here. So let's say you have the same setup, but both positive and neutral are, let's say these are the correct classes. It's okay to say neutral, it's okay to say positive. So what you will do here is you will model these as 3 problems. One is whether am I getting this positive correctly, right? So you will have a sigmoid that tells you that, okay, this is 0.9 positive, 0.1 this is not applicable here. Similarly for neutral it might say 0.8, 0.2, right, which is saying that there is a 80% chance that neutral is okay label for this, is an applicable label for this. Let's say for negative it says 0.7 it is an applicable label, 0.3 it's not an applicable label. So your loss will be, so what is the correct answers here? The correct answers here are 0.9, 0.8 and 0.3, right? You would want to say no here, this is not the label that applies, but these are the correct labels. So your loss will be negative of log of 0.9 plus negative of log of 0.8 plus negative of log of 0.3. So this is close to 1, so these are much smaller values than this thing, because here you actually messed up, right? You said that this is positive, neutral and negative, but your data said this is positive and neutral. Yeah, this is given by your model, this is not your choice. So you are saying change this to 0.1?
I'm saying that how to penalize it even further in terms of not saying it says point, it should be, yeah, from our data set it should be 0.1, but it says 0.3, that itself is wrong.
Yes.
So how would you penalize it even further?
Yeah, I mean, so one question is like, do we need to penalize it further? In practice this works really well because this will drive the model to, like, this is a very high value, it will make big updates in the model such that after some time you will get a 0.0001 here and a 0.999 whatever right here.
So what if it was 0.6, 0.55?
So 0.55 also will, like, it's just a function of how big your, like, how poor, how badly wrong you are and how much should I punish the network. So if you were like if this model said 0.99, this is also the correct output, you will be like, how dare it, like this is absolutely wrong, I will have a very large loss. So this loss function basically has that mechanics inbuilt, and it kind of like takes care of that for you. Having said that, nobody is stopping you to use only this loss. You can come up with your own loss function. Let's say your loss function could be, I will have a like you could have a loss function where, let's say, messing up with this class is a lot more severe. So missing detecting cancer is, let's say, a lot more severe than falsely detecting cancer. If I tell you that looks like you have cancer, you can at least go and get a second opinion. But if you had cancer and I said, don't worry about it, everything's good, like it could cost you your life. So there might be cases where some classes are more important than others. So you might want to like have a coefficient that, let's say, says 100 times this. So if you are wrong on this class, I am going to penalize you 100 times more. If you missed detecting cancer, that's 100 times bigger sin than telling someone they had cancer when they did not. Right? Okay. So far we kind of have looked at options where we are manually extracting features. We are manually extracting features. Yeah, let's see. So here we decided that we are going to write 3 features. How many positive lexicons, how many words are there, and whether there is a no. Let's look at some automatic ways to do that. I mean, we don't want to be handcrafting these features, and if your features are not good enough, they are not expressive enough, then your model will not be good enough, right? It is a function of your features. If you are not, like if you miss the word amazing, then it will not detect that because you did not give that as a feature. So let's look at some better ways to do this automatically rather than relying on you. So one way to encode this is called one-hot encoding. So for every word in your vocabulary, let's say you have V vocabulary items. Let's say your vocabulary is 25,000. You're closer to Shashi Tharoor than me. So you can speak a lot of words. Now, for every word, you have a special index corresponding to that word. And let's say for amazing, that index is 1149. For great, let's say that index is 73. So by one-hot encoding, I mean is in a large vector, if the word is amazing, then only this will be positive, equal to 1. Everything else will be 0. So it's a one-hot vector. It's hot only when it corresponds to your index. So for amazing, 1149 index will be 1, everything else will be 0. Similarly, if I had a vector for great, only 73 will be 1, everything else will be 0. So this is a very simple way of representing words. It is also dumb because great and amazing are close, but if I look at their similarity in terms of cosine similarity, the dot product will be 0 because they are all different indexes. It's not capturing any of this notion of great and awesome and amazing are similar words. So it's not it's not the best way to encode vectors, but let's for now think that at least it's an automatic way. I don't have to craft features, every word has a particular index. Similarly, you could say that I have a bag of words. So to represent sentences, let's say let's say if we go back and say if we want to represent this sentence, right, desert was good. So we'll say that this is nothing but a bag of words. So let's say if desert was index 99, this was index 107, this was index 445, then my vector will have ones corresponding to 99, 107, and let's say 445. So everything else will be 0 except these 3 values. So this is really like a bag of words. Like you are not capturing order. If the sentence was good was desert, you will still end up with the same representation. If the words are repeated, great question. So in bag of words there are 2 forms. One is called a count vectorizer, where you actually count. So if the word was desert was good, really good. So then one way to represent is I am going to take the good, it comes twice, so I am going to add. So I am just going to, instead of say bag of words, I am saying count of words. So both are acceptable. You could either say I only care about presence or absence, or you could say I care about counts. Different applications, one might be better suited than others, but that's perfectly legitimate way of encoding a sentence. One second. But is this clear? Like, is the bag of word representation clear? Question, yeah.
Desert that have different meanings, will they have same encoding, for example?
Yeah, good question. So different sentences that have similar meaning, will they have same encoding? Not as per this format, right? So if I said ice cream was great, desert and ice cream have no relation, great and good have no relation, they are just different indexes in this particular vocabulary.
A desert in itself means different things.
Yeah. So great question. So a word could be polysemous, like a remote could be a remote village or a computer remote. That is not taken into account here. The same remote is used, like there is only one identifier for that. Question?
Is the order of words also ignored?
It's ignored, yes. Order of words is also ignored here. This is a very simple way of encoding. We will come at better ways of encoding, but here it is ignored.
So, let's say you have a lot of data which keeps telling about desert only. What if the factor of desert itself gets recognized as a positive?
Yeah, great question. So the question is, let's say desert happened to frequently co-occur in positive things. Would that mean desert is positively associated? The answer is yes. So let's say if Shah Rukh Khan happens to do good acting and most of his films get positive reviews, then Shah Rukh Khan as a factor is a positive influence to the prediction, right? So the model does not know whether the word good is driving the prediction or Shah Rukh Khan is driving the prediction. It sees all of those as numbers essentially, right? Yeah. Yeah. So which is where biases could also come. So let's say if you're doing, let's say, automated hiring, and everybody who said girls cricket team was not hired, then maybe the word girls might carry a very negative connotation. So you have to be very, very careful, because these are again systems that are purely associative. They look at numbers and they associate them with the class. Numbers that frequently co-occur with the particular class get associated with that class. So yeah. Yeah, so those things can also be done, but one other simpler way is you augment your data, or you get a more representative data set. So if you happen to only interview very few, let's say, women candidates, and somehow they did not make the cut, rather than having a feature that women, like having the model assign a negative weight, you should interview more women so that you have a representative sample, right? The whole thing as one hot vector. Yeah, you could potentially, but for every 3 words there would be vocabulary cube possible combinations. So that space really blows up. So if I allowed every trigram to have a one hot vector, then I will have to have v cube number of values here, which can be a lot.
How this will compare with the that I mean, of course, in space complexity, this is better.
Yeah.
But what about like why we are using this bag of how it is advantageous?
So okay, so yes, on space, so it's not like just this is better on space. If you were allowing a v cube number of representations, right, like if each base unit was 3, then v cube for even a modest vocabulary of 10,000 becomes a billion. That's just a lot. That's just like practically not possible, infeasible, right? And the other issue is that their desert was great and desert was good will have a different index. Here at least you are sharing desert was between the two. So here the similarity, cosine similarity between desert was good and desert was great is non-zero because desert was is common.
In a same sentence, if a desert has different meanings,
Yeah.
we are using desert as a sweet and desert as a
Place.
where it's too hot.
Yeah.
So somewhere we are talking about positive
Yeah.
things, and somewhere we are talking about negative things. What about the model is C? Is a positive thing or negative thing?
Yeah, great question. So model will not have the ability to conceive that this could have two meanings, right? It will always, like by design you are mapping it to one index. So there were older systems which would do what is called as word sense disambiguation first, and based on whichever sense of the word is being used, they will have a different identifier for it. So Apple the company was a different index, Apple the fruit was a different index. But that's not how we do, that's not how this representation works, and that's also not how, let's say, GPT works right now. But it was tried and done.
Instead of having real numbers here, what if we use complex numbers where we can at least represent a diagram and once.
So diagram also, I think the complexity, space complexity blows up.
Of the real numbers, 1 and 2, like can I make use of 1 plus j something?
So basically you can use it, but if you have, let's say, a plus iota b, and if this can be v and this can be v, and all cross combinations are possible, then you are ending up with a similar problem, right? Okay. So another form of representations is what is called as embeddings. You might have heard of word embeddings or embeddings. Those are like, I don't want to be in the business of giving this. I will just let a model create an embedding. So how it works is, let's say you have a one hot vector. Let's say this is for the word great. So this is a, let's say, r cross v. Okay, so this is a one hot vector. Now you are saying that I will randomly initialize a large vocabulary cross d-dimensional embedding matrix. It's called an embedding matrix or a lookup matrix. Right, and this will be, let's say, random to begin with. I will multiply this with this embedding matrix. So v into v cross d, I can do that multiplication. I will get a d-dimensional output. But what this multiplication will essentially do is it will pick the third row for me. Is that clear? So if I multiply this, like if I multiply this, I'll get 4.3 and so on, right? So convince yourself that this is just a way to pull out a row from that matrix. This is a new matrix called embedding matrix that you have initialized randomly now, but it will, like all other weights, be trained as a part of your neural network. So rather than you having to give representations, this model for the word great will have that representation 4.3 blah 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 to begin with, but that representation can be updated like all other weights, can be improved like all other weights, and by the end of neural network training you will have a much more refined vector, refined representation for the word great. Yeah, so the dimensions is a hyperparameter. So you could start with something like 300, 600, 1200. This is just a hyperparameter. You try different options and see which one gives you the best performance. Actually, in practice, the question really is, what is the biggest dimension I can, which is the biggest dimension I can hold in my GPU memory so as to not go out of memory. Can you switch it on once? Can you switch on once so that I can see the question? I think there was a question on streaming. 1 second. Do we have 3 vectors? Hello, can you show me the question again? So there is a question from Saurabh. Can you, do we have 3 vectors of 1 vector? Can you clarify, Saurabh? What do you mean by 3 vectors of 1 vector? So essentially for a word like great, you will pull out this row which is of d dimensions. So every row will have, so every word will have ultimately a d-dimensional vector.
Whenever, even though you randomly initialize this embedding matrix, and you said that you will train a neural network, but you need supervised data to learn this.
Yeah.
But if you don't know what embeddings are,
Yeah.
to train the neural network, how will the neural network learn this random way?
Yeah. So this will become clear when I show you the network and show you the task that I'm using to train it. So we were talking in the very first class about language models, which is I think what the course is about. So if we were to do language modeling, which is the task of predicting the next word. So let's say here I am looking at these 3 words for all the, let's say the correct answer is for all the confusion, right? Or for all the drama. So let's say that is the next word that is supposed to come here, right? So you will look at, let's say, the last 3 words, build, let's say this is 35 index, this is 992 index, this is 451 index. You will get that row from that particular matrix that I showed you, and you will get an embedding vector for these 3 words. Now these 3 words will be inputs to a lot of perceptron or neural units, which will further be connected to another layer to give you a vocabulary number of classes. Like we said, positive, negative, neutral, here every word could be a next possible candidate, right? Because anything could come here and we want the system to be able to generate every possible word. So you have a vocabulary class as your output. So language modeling is being modeled as a K class problem where K is your vocabulary. And now if in the data the answer was confusion, your loss will become what? Can people tell me what will your loss be? Minus log of probability of predicting confusion, right? So if the model did not say confusion, you will penalize it, you will update it, including this embedding vector and matrix, right? So including this matrix here will be updated if you are not getting a good enough loss. Like everything by default will be updated. So just like you backpropagate all the weights of the network, even this matrix will be updated. Now the question is, where do you get all this data from to do this much updating, right? I mean, this seems like too good to be true. But remember that your internet is full of text. There are trillions of tokens which you can pose as next word prediction problems. So for every fourth word in your internet, or for every word rather in your internet, you can say, looking at the last 3 words, I'm going to make a prediction. So if there are 20 trillion tokens on the internet, you have 20 trillion data points. So this is also called as self-supervision. So no human being gave you annotations of good, bad, negative, positive. By the art of writing, you got this data for free. Because somebody wrote their poems, their reviews, their rants online, you can now perform this task. You can now update your neural network using the data that is out there in public domain.
So, like, what is the lower bound on the D? Because like, if the size of the vocabulary is 50,000,
Yeah.
I can fit all the points within a circle. As I move to the 3 dimensions, then I can fit all the points within the volume of a sphere. So, what is exactly the lower bound on the D? Is it accuracy or?
So, okay, great question. So how should we think about D? So if D is 1 dimension, then every word is getting represented as a number, which is not very far away from here, right? This is already a number. So it really depends on how much knowledge about a word you want to encode. Higher is the better option because you want to capture lots of things about words. So to give you an example, a word like knife, it can be used to murder someone, it can be used to cut a vegetable. It can also be a symbol of, let's say, protection or safeguarding. So many things can be associated with the word knife. Like a lot of things come to your mind when you think of knife. So depending upon how powerful your model is, your D will be large. So let's say GPT, Ds are close to tens of thousands. But if you think of a theoretical lower bound, just to identify and distinguish a word great from any other word, you just need one scalar essentially. Okay.
Embedding, like this embedding layer, can it be learned separately from the whole neural network?
Yeah, great question. Can embedding layer be learned separately from the neural network? It is possible to learn embeddings through other mechanism and fix that embedding. So that is also possible, but these days it's rarely done. So there was a time between 2015 and 2018 where people had found out a way to train word vectors. The 2 popular options back then were word2vec and glove, which people had found another way to train, and they were very good vectors. So people used to load these as word2vec vectors. So that matrix was word2vec. And people would typically not change that, and everything after that will be tunable. But that is not a common practice anymore because we have better compute and access to bigger data sets now. So we don't have to do that now. Okay. Okay. I understand now. So I was talking about, so the question I think Saurabh really wanted to ask was something different. So here we were talking about, so the question is, when we're talking about one hot vectors for a sentence like desert was good, are we talking about 3 vectors or is this 1 vector? So this is 1 vector, and this representation is no longer one hot encoding. It is called bag of words, and each one corresponding to its own like all the words, all the active members of this vector correspond to one word in the sentence. So one word corresponds to, let's say, desert, one to was, this is 107, sorry, and one to good.
So in the diagram next, we represented all the words as vectors and perform vector algebra. Now the last stage where you got a vector, how did that exactly get converted into a class?
Okay, great question. So at the end, I got a R to the V dimensional output because I have these V number of output units. I will perform a softmax to convert that into a vocabulary sized probability distribution.
So each word has its own vector because it's all vector operations.
Yes. So that is at a feature level. Once this has been fed at different hidden units, then output of every hidden unit goes to every unit in this layer. So the role of words is kind of like encapsulated here.
What does the output look like? Is it going to be another vector?
It's going to be another vector of size vocabulary, which contains the probability of producing every word corresponding to that index. So let's say the value of 35 is 0.02. The interpretation is that the probability that this network assigns to predicting for after this is 2%.
When we are doing machine translation, so does that mean our vocabulary has to include the Japanese, French?
Yeah, we will come to machine translation in the next after break session. I'll explain that. Yes.
So when you do hard encoding, basically out of 4 V points, you have only 1 point. I mean that you repeat for every word, right? That row you repeat for every word if you want to write that. So is it not too much of computation just to give importance to that one word and remain zeros, and because in terms of computations?
Yeah. So I think so this is a matrix multiplication, right? So if this is an X, this is an E, this is just one matrix multiplication. And if you have, let's say, 10 words, right? So let's say X is a matrix rather than a vector, then you can also directly do this matrix multiplication and look up 10 words in one go using a matrix multiplication. And
But end of the day, it has to compute that V into V again. Because that
so at the end of the day, yes, it has to compute a V dimensional output. So softmax, this last step is definitely a bottleneck. It takes one of the most compute intensive steps, yes.
In the embedding matrix, would it be wise if we have some handcrafted
Yes. So would it be wise if we had some handcrafted features in the embedding matrix? If you have strong intuition or strong requirements, you can have that. It is not prohibited, but that's not typically the normal practice. Yeah.
it's just about the question about that these numbers are like V cross V and D cross V.
Okay, so the numbers are not matching. Okay, so this part is clear, right? So there are 3 words that we are looking at. So we have 3 one-hot vectors. Now you have this matrix that is, I was showing you a V cross D matrix, but this is a D cross V matrix. They're multiplying it. They're doing E to the power X rather than XE, EX rather than XE. But you will get 3 D-dimensional vectors. Sorry. 1 second, where were we? Okay, so you will get 3 D-dimensional vectors. Is that clear?
They are separate 3-dimensional.
Yeah, so this vector is for the word for, this is for the word all, this is for the word the.
So this is this
Yes, yes. So this is a 3-gram feed forward neural network. It will always take last 3 words. It cannot look before that, and it will always predict the 4th word essentially. So instead of like having handcrafted feature like desert, good, bad, you are learning features as a part of this network, and it's a feed forward network.
So at the end, when the embedding matrix is created, will it also take into consideration similar words which are being said?
Yeah, great question. So because it so happens that words like the movie was great, the film was great, similar outputs are expected when movie and film occur in your context. They will, as a virtue of training, happen to have similar embeddings. So it's not like you are not deliberately forcing that, you are not designing for it, but that naturally happens because that is easier for optimization.
If I take the cosine similarity, then I get a
Yeah, you will get you will find that film and movie are maybe closer than film and Apple.
But what if we extrapolate that to sentences? So for example, I love apples very much and I hate apples very much.
Yeah.
One word is different.
Yeah.
So
So we don't talk about sentence embeddings here so much, but I'll come to a more elaborate architecture where we will talk about that, and I can explain that in a bit more detail. So this paper, this diagram and this architecture was introduced by Yoshua Bengio and some of his students, I think in this landmark paper in 2003 or somewhere between 2003 to 2007. This is a point of time when nobody was seriously doing neural networks and wasn't seriously applying it to the task of language modeling. And they had shown that this is quite competitive in terms of performance. But I think only in 2013-14 when people started scaling these systems up, it became very apparent that this was the way to go. Yeah, so this is not very far away in like broader history of computer science. So we are like 20 years from here. Yeah.
Does this vector, using this vector, solve the issue that you showed the example of apple being a fruit?
No, it does not. Right, because yeah, like we are giving the same index to the word apple, fruit, and company. So yeah.
No, but when you see the embedding, wouldn't it be closer in one dimension and a little farther in another dimension? When you actually
Yeah.
visualize it, it would be.
So what actually, so in like these days and even for this model, we never give a different ID for the fruit and for the company. But the model is expressive enough. The model has seen apple in multiple contexts, some of which are fruit related, some of which are company related. So the model is able to assign some components of this d-dimensional array to serve as a fruit, some components to serve as a software company. So that somehow automatically happens because the model is forced to produce the correct output again and again. So when it sees the CEO of Apple was, like those parts of that embedding are used compared to like when you're saying that I bought bananas and apples. Okay, so let me move forward. I'll take more questions. But one thing you are noticing is that we can't do more than 3 or more than fixed number. So it's a K-gram language model. It has to have a fixed window. So ideally we want to go to a state where we can consume multiple sequences of variable length, right? So this one has a lot of problems. One is it cannot capture long-term dependency like we were talking about in grams, right? So if it is 3-4 gram, it can only do that. So this is where we bring up recurrent neural networks. So time flows, like language also flows, so there is like a temporal component of it, right? You want to handle variable length sequences. So this is a very, very simple architecture. It is slightly different from a feed-forward network. The special thing about it is that at time step t, it consumes output of t minus 1, which is why the word recurrent. So basically it eats up its own output, right? So what does that even mean? Like if you were to unroll this, this is what it looks like. So this is the same network, same A with the same weights. So this A is not different from this A, but let's say you passed the embedding of first word, you get some output here, which is how to get that output I will explain later. But that output is now the input of the second RNN. It is the same RNN as the first RNN, but it is the input to the RNN at the time step 2. Similarly, at this time step, the output from the previous time step is an input. So as you can imagine, by unrolling this, you can run this for as many number of steps as there are words in your sequence. So if you had only 3 words, this will be your network. If you had 4 words, you can use the you can add one more. Right?
The operation of A is same in every case.
Yes. So the network A is the same. I will define what that is and what operations it actually does.
So,
Question?
what will you do if you just if you have let's say if you design this for 10 inputs but only 2 or 3 inputs?
Yeah, it will still work. Let me explain how this works. So it can handle variable length sequences. So these are the 2 operations that a simple RNN does. It is also called as Elman RNN because this is the person who introduced it. So it does 2 things. So it has 2 inputs, the xt that we were talking about here, right? And the output, the hidden output from t minus 1. So this is the h0 here, the same h0 here, same h1 here, same h1 here. So the output that you're going to produce is this input to the third RNN here, RNN at time step 3 here, right? So it will take at time step t, it will have 2 inputs, xt and ht minus 1. What is xt? Xt is the row or the embedding that you have pulled out for the tth word. So if the third word is good, it is that row in that embedding matrix, that vector. Okay. What is h2 here is the output of the RNN at time step 2. So it does very, very simple things. It basically multiplies this with another d cross. Let's say if xt is r to the power d, w is, let's say, r to the power d cross d. Let's just simplify this. So it just does a weighted multiplication. Similarly, ht minus 1 is also transformed by another weight matrix. So these weight matrix are telling you how you should weight every single feature that is there in xt and ht minus 1. How you should see the third dimension versus the fourth dimension versus the ninth dimension. So if the ninth weight corresponding to the ninth dimension is closer to 0, that means it will have less influence in the final output, which is how you should implement, how you should think of this products. And this G and F are just non-linearities. You don't want this to be a fully linear network. So you have non-linearity. G and F are just simple functions that are non-linear. You can think of them as ReLU functions or tanh functions, right? These are just very, very simple functions. So RNN is nothing but it takes two inputs, xt and ht minus 1, transforms that using a matrix U and W respectively, adds them and takes a non-linearity. Now this gives you an ht. Before you finally output it, you also, let's say, want to project it. Why is this needed? Let's say your dimension is 300, but you want to output a word in V dimensional space. You will have to project it to a V dimensional space. If you just want to say whether every word is positive or negative in a given context, you want to project it in 2-dimensional space. So this is like for projecting to K final classes. So let's say if you want to produce words, then this will be D cross V. So this is very simple. If you want to unroll this, this is what it looks like, right? So this is the operation with x1 and h0, right? The output of this is transformed through V and goes to x2, and this is the unrolled version of that.
We are actually learning the U, V and W.
Yes. So the parameters of this model are U, W and V. There is also an embedding matrix here because that's what is giving you the embedding, which I have not shown, but that is also there. E. So these are all the four unknowns, four unknown matrices that you will learn as a part of this network.
But this is like only one is there. And
Yeah, great question. So this V is not different from this V. This W is not different from this W. It's the same matrix, which is why you can apply it for any number of times. If there was a V1, V2, V3, then I'll have to tell you how many V's are there, which will predetermine how many words can you consume.
So in that case, like when we are backpropagating, has to remember.
Yeah. So we'll look at how to backpropagate this, but at least I want you to think about this, that this can consume a variable length sequence just by virtue of unrolling an RNN. That is your choice. You are just saying that I'm going to use the same W. You are doing this computation yourself, right? So in some sense, you are writing this function in a loop for t equal to 0 to n. You are going to keep applying this same function with the same U and W. The only things that will change are X and H because your inputs are different and as a result your H's are different. Yeah, please. Yeah. So there are two notions of output. One is called the hidden state. People sometimes also call this as an output. But technically the output is when you've transformed into the vocabulary space, if you're making a vocabulary space output. Like if you're predicting words, if you're predicting sentiment of 5 category, then the output will be 5. So hidden output is this thing that is passing along across time, and that is the same thing that is later also projected to, let's say, give you a vocabulary dimension output. So if the X is clear, right, if X is a row of that embedding matrix, then hidden dimension is given by this formula. If you just look at, sorry, I think butchered it, but this is the formula, right? This formula determines what H is. Okay. So basically all that is to be remembered about what is important in your context should be relayed here. So it will come through H, not U. So like U, W are parameters that you will learn, which will also tell you how to treat X and H, which will of course be a function of the context.
So in the unrolled version of this,
Yeah.
so what we can just see that U is being passed out.
No, no, no. U is not being passed out. U is the same U that is being applied here. So basically, so H is the output here. H1 is the output here, which is transformed by U. So H is essentially being relayed, but it is transformed by U. So last question, and I'll stop and take a break, but we'll come back and do this. Yeah.
How will you select the value of H0?
H0, great question. So maybe for now you can think this is all zeros. So all zeros will not change the first part. So when you're starting this, this will have a 0 contribution, but H1 will have some meaningful value based on X0. Okay. So H0 is 0 to initialize. Okay. So we'll come back from this and we will go from here. Okay. So we'll take a break and we'll resume at let's say 12:05. Okay.
also. Sometimes it's I already this also turned on.
Okay. Thank you. Hello. Hello. Okay. Hello. Is this better? Can people hear me? Yeah. Okay. So shall we get started? So let's quickly revisit the RNNs. These were the two equations we were looking into. Right. So these were the two equations we were interested in. So it's a very simple formula. You just transform your xt and ht minus 1. These are the inputs at time step t, and they're transformed by w and u matrix respectively. And then you take a nonlinearity which gives you the hidden output at that time step ht. Ht can be used to get you the output you deserve or you want. So you can transform ht into whatever dimensional space you want through a matrix multiplication, and let's say f could be softmax if you want to convert them ultimately to probabilities. F could be softmax, right? So all of that is possible, and like if you are maybe a bit like if this notation is not very comfortable to you, how these matrices are being multiplied, I would say write it down on a piece of paper, open these terms, and you will, I think, become more familiar. So it is a very common operation in deep learning to transform a vector into, let's say, a different space, transform it back into another space, apply a non-linearity. So this is something I think being comfortable with is worth it. Yeah. So I mean, this dimension d of hd, right? It basically essentially controls how much space. So the question is, if we were to reduce the space or the dimensions of ht, are we going to lose any information? The answer is yes. Like if you can imagine that if it's only a one-dimensional number, the total number of bytes that it can encode is very less. Right? Similarly, if you had a much larger space, you can encode more information. That might help. Question?
For example, if you go to, let's take h of 100, obviously we'll start from 0 and go to 199. So as we approach to the h of 100 or to that 100 instance, since we apply a lot of non-linearity,
Yeah.
so won't we lose the context what we wanted to achieve in the first place?
Yeah, so that's a really great question. The question is, if we keep applying this to, let's say, h1, h2, all the way till h100, will h100 have any information about h1 at all? Will we lose that information? The answer is yes, quite likely we will not be able to retain information for these many time steps. In practice, like RNNs are like 7 to 10 steps of information can be, let's say, reasonably encoded. But being able to attend to information a long while ago or a few time steps ago is very challenging, because this is sequential in nature. It goes left to right, one step at a time. So that is an inherent challenge. So one challenge is it's sequential. Second is longer contexts are harder to capture. I mean, this is much longer than a typical n-gram, right? N-grams are 3 or 4. If you go to much higher n-grams, then there are like severe sparsity and space constraints. This can easily model words that are, let's say, 4 or 5 time steps away. But by longer, I mean, let's say 10 plus. Contexts are hard, right? Hard to capture. So these are the two major weaknesses that transformers, which we will study in some time, solve. So I'm glad that people are already able to identify these as limitations. But let's, before we go to transformers, let's look at a few more properties of RNNs. So one thing is okay, we've introduced RNNs. How do we use them for language modeling? This is how we would do that. So we typically start with, let's say, whatever words we have, we get an embedding for them. How do we get an embedding? We pull the row corresponding to the word we have. So if the word says 441, we pull the 441st row out of that embedding matrix. It's also called as a lookup operation. Now you have an embedding. This becomes your x1, x2, x3 and so on, right? This is your h1, h2 and so on, right? Now this v will transform at a vocabulary space, will transform the hidden dimensional space to a vocabulary sized space. So you will produce a softmax over vocabulary. It gives you the probability of which word could come next. Again, the task is the same, language modeling, which word can come next. So here the loss again is also very, very familiar. We have done this. It is negative log of probability of predicting long. If the next word is long, we want to predict that, right? So if we started for this, so long, if long is supposed to come after so, we predict long. So the probability, so it's log of P of long. Y of long is just another way of saying what is the probability of long. Question?
Why we are not considering the given the first word was so and then
Yeah.
we are getting
So is the first word. So there is no previous context here. But when we are predicting the second output, both so and long are being factored in. So long is directly an input as x2. But the hidden state after consuming so is also an input to this, right?
so in the loss also we will consider that only
So the loss will just be negative of log of probability of and, but remember that to come to this loss value, you are using information about the word so, because it is being passed on through this hidden state. So let's say if something about the embedding of so is not right, you will update that also based on the loss that you have incurred at time step 2. So if you are doing backward propagation, the loss that you are incurring here will go here as well as will go here, right? Because it is a function of this as well, right? The h1 is a function of x1. Output of time step 2 is a function of h1. So this is a bit more complex than the small computational graphs I was showing you where E was a function of D and A. But you can extend this mentally in a way that everything is being used to compute that output. So it's a function of all those inputs, and hence updates will touch all those things, right? Updates due to loss of log probability of and will impact even the embeddings x1. Question? How would the gradient descent look like in this case? Exactly the same as it looked like in every other case. You will have to compute d of log loss. So loss is negative of log probability of and And now you will see how does that probability change with respect to changes in embeddings of 1. Right? So if this value was 0.981, you will see, what does this partial gradient tell you? It says that if the value was slightly different, how would my loss change? Right? So if the loss is positive, if increasing this means you incur a more loss, then you will rather decrease this value. That is what gradient descent does.
So let's say you go to the next step, then you have to go all the way back.
Yeah. So your total loss is a average of loss of first term, second term, third term, fourth term, fifth term. So this is written here. 1 upon t loss at every time step. So again, like if you imagine or think about each and every term, it might become quite tedious, but this entire loss is a function of a lot of inputs here. Good news is that PyTorch will take care of all of this for you. You don't have to analytically or mathematically compute gradients by yourself. PyTorch does that for you. How come it's so easy? Internally, it's a computational graph. Like it's complicated operations, but each operation can be mapped to simple operations internally in machine code, and it just has to do backward propagation. Right? Yeah. So gradients vanish here. It's a problem with many, like let's say whatever loss is coming from here, it has to go through a lot of steps. There's a lot of multiplication that happens on the way. It can happen very well that some of these gradients become arbitrarily small. So it's a common problem to observe. So there are some advanced recurrent neural networks, like one of them is called long short term memory, LSTMs. They have a special gating mechanism to kind of avoid some of that problem, but they're also not free of vanishing gradients. It is a problem. So transformers happen to be much better at it because of some properties which I will explain in some time.
So what if I take the hidden state of the first one and
Yeah.
connect it directly to the output?
Yeah. So you can build a slightly different architecture where instead of saying H1, like my current recurrent neural network is contingent on the past hidden state, you can make a choice that it will be contingent on the past 2 hidden states. That is also possible. But you might be tempted to then do it for past 3, past 4. So it becomes a bit arbitrary, but at least people have used what idea you are suggesting in. So this is like from time t to time step, let's say 100. But people have used this idea in depth. So if you have 100 layers, people typically will connect the output of the first layer directly to the 5th layer. So these are called as highway connections or skip connections. This is exactly meant to, it's exactly using the idea that you just suggested to be able to get rid of this vanishing gradients problem, so that there is a direct mechanism for the gradients to flow back. So this has nothing, so the question is, can it be applied to the unsupervised part? So this has nothing to do with unsupervised. All of this requires supervision, just that this supervision is coming for free because we are using the next word prediction as a signal, right? We are not getting people to annotate stuff for us. It's already English written text that we are using. Yeah, the highway connections or skip connections are not dependent on the nature of supervision. Yeah.
So is this the reason that why we are not using the prior probability of like in the P and we are not using P and of long? Because given that long was the previous word and then we are getting
Yeah.
that probability will get reduced. So because of the architecture of RNN, we are only using the probability of and.
Yeah. So the question is, like, at time step 2, why are we using in the loss only the probability of and? Why not probability of long and? Probability of and given long. So we are using the probability of and given so long because they are inputs to the network. They are like it's like we are conditioning on this x1 and x2. So RNNs give you probability distributions conditioned on the text. If you change your text, the probability distribution will change. So the AND that you are seeing is conditioned on so and long.
Sorry, I mean in the loss function.
In the loss function, the probability of, let's say you made a terrible error of predicting long. So you have already punished the network for it, right, in the first step. You don't need to do it again in the second time step. So there are multiple ways to actually go about training this. One approach is that whatever the network has generated, I will use that as my second input. Okay. Another approach is I will spoon feed. I will give the correct input regardless of whether the model has produced the correct output or not in the previous time steps. So the spoon feeding approach is called teacher forcing. You can imagine why. So that is what is typically done, especially during the start of the training. At the start of the training, the models are quite random. They are producing random output. You don't want to be taking random output as your input. So as models are trained to some degree, you then start to move to the case where you are reusing the model output as input. Like you can put in, let's say initially you said, so thanks, right? So let's say your prediction was thanks. You have punished the model, but the model prediction is still thanks. So the first option is I will use thanks as my x2. But in your input, the sequence is so long and thanks. So teacher forcing mechanism will say that, okay, use long. It's okay if the student has made a mistake. I will spoon feed. At the same time, when you are generating text, let's say when you are using this model to generate new input that you have not seen, you don't have that luxury of spoon feeding. You have to make your students really like work in the wild, right? So whatever they generate, they will consume that. Question?
So, if because of for, it changed the W's and all the other values from that.
Yes.
Now, do we have to calculate new loss for again long and times and all of those, because that can have impact on next word also.
Okay. So you're saying because of mispredicting for, I already updated some of these parameters which may have changed the previous predictions. So should I account for that? That's a great question. So in one cycle, first of all, in many networks and for many examples, you will go over your examples multiple times. So there is multiple epochs of training. So in one go, you will aggregate and average your loss. So the updates to, let's say, your embedding for so is determined partly by the loss from long, but partly also by loss for for. Whatever is the net averaged loss will essentially be updated. So for is impacting so, but that operation happens once. So you take the average once and update. You don't think that you update and then you come back to that example later.
And you come back to the later, then you start again from so. Then
Yes, exactly. So once you're done, you come back and redo this essentially. Yeah. Okay. Great. So so this is now clear how RNNs are being used for language modeling. You know how they're being trained. You know the loss. You know how they're being once you have a probability distribution, you can either take the maximum token, which has the highest probability, and use that, or you could say that if the probability is 0.4, 0.3, 0.2, 0.1, I will sample based on that probability. So if a token has a probability of 0.2, it will be sampled 20% of the times. So both approaches for generation are okay. These are called decoding or sampling strategies. The first one is you pick the maximum. It's called greedy decoding. The second one is you sample. It's called multinomial sampling. Okay. So when you are generating, as I was saying, whatever is predicted has to be consumed. There is no other option. You don't know the future. Similarly, you need not predict words. You can predict something else. So there is a classic problem of sequence labeling. Let's say you want to label a sequence, whether it is a noun phrase, a modifier, a verb, a determiner, a noun. This is sometimes useful whether, let's say, you want to know what verbs are used in a resume. People say that you should use bold active verbs. Or you could also say that I want to label my sequence in such a way that I'm able to extract named entities. So people's names might be labeled as begin of name, intermediate of name, end of name. So these are standard tagging tasks. But the point that I'm trying to make here is that you need not use an RNN for language modeling. You can use it for sequence labeling. Any kind of labels are okay. Okay. So you can also, by the way, use an RNN for classification. So you are not necessarily outputting or using the outputs at every time step, just that the last output, HN, which supposedly has all the information because of the recurrence relation, has, let's say, all the information about the sentence, and now you use this as a features for a feed forward network. So similarly, like you were working with this sentence like desert is good or desert was great, you can have that as your input, run an RNN on that input, use the last state as features for your feed forward neural network. So if you go back to this example that we saw earlier, right, instead of we making features, you can potentially use a RNN to give you the final hidden state after consuming this sentence. Now this also does not run into the problem of fixed features or does not run into the problem of having to either create a list of features yourself or relying on, let's say, a fixed window. It can dynamically consume as many words are there in your review, which is, I think, the biggest advantage of a RNN. Okay, so RNNs can do sequence classification. It can, let's say, do sentiment analysis. It can do topic classification. Yeah, so the target when you're generating this, so when you're training the model to do language modeling, the target is producing what came next as per what was written in the book or as per what was written on the internet. Once you have trained that model, only then can you start to generate from that model. So there is, when you're generating, this is not training. It's like you're just using the model to give you new output after you've trained it. Okay, is that clear?
What about for classification?
Yeah, for classification here also you will have a loss based on whether your class output was correct or incorrect, and you will train it, but after you have trained it, you can pass a brand new movie review and ask the model to make a prediction.
What is the output of the RNN that is going?
So like you were predicting earlier in vocabulary space, here you will predict in, let's say, 5-dimensional space. So this space could mean highly positive, positive, neutral, negative, highly negative. So if these are your 5 classes, your output from this feed forward network will be a 5-class output. Question, yeah?
Can we take this instead of the last hidden state? Can we take it like at around regular steps, like 5 or 7?
Yeah, you can take here, but this, so the question is, can I, instead of going all the way till the end, can I take intermediate outputs and do sequence classification? Yes. So you can do, so there are approaches, so it's called pooling. So instead of relying HN output, one idea could be like I'm going to do average pooling. So I'm going to take an average of all the hidden states, and that is going to be my features for my neural network to make the classification. Yeah, all that is possible. Yes, question?
Continuing a question about generation or generative capability of RNN. Sir, is this true generation? Because we are not sampling from a distribution as we do in case of say other generative.
So what do you mean by true generation?
For example, we know that an autoencoder is not a generative model.
Yes, yes.
Similarly, are we also not doing something similar with RNNs? We are not really sampling at each point,
Yeah.
I would say, and then
Right. So when we are training the model, we are basically just training the model to assign the highest possible probability on what actually came next. Now the model has a mechanism to assign probabilities for what could come next. Now you are using that probability distribution to generate outputs. You could either say that whatever that distribution recommends, I'm going to sample in that proportion, which is what is typically done. So these are generating models. These are called auto-regressive generative models. This is like the G of GPT, right? Generative.
does it work well for generation?
Yeah, this is not bad. RNNs for language models are not bad. In fact, there is a post by Andre Karpathy which is dating back to 2015. It says the unreasonable effectiveness of RNNs. So you should check it out. He has a lot of interesting analysis. Yeah, these models are not terrible at all, even though they look very, very simple. They can generate much better output than 3 gram, 4 gram models.
So in that RNN for sequence classification, so do we train them separately or do we
No, it's all. So the question is for sequence classification, is this RNN part and the feed forward network part trained differently? The answer is no. They're all trained together.
So like if I have one sequence where there are only 8 words about the review and another sequence where there are 50 words about the review, we are compressing everything to a same HN which
Yeah.
will be having the same dimension.
Yeah.
So it will become a bottleneck as we
Yeah. So great question. So if the sequence's length increases, like it may happen that H is no longer sufficient to encode, and the architecture is also maybe because of a lot of matrix multiplication is not capturing enough information. All those are valid concerns. These are concerns that transformers take care of. So we will come back to that. Yes.
Can you reiterate the point on the advantage of RNN that you're saying, like for sequence classification, you don't need to specifically choose the output dimension?
No, you do have to choose the output dimension. It is just that you don't, you have variable length sequence and it captures context. So compare this to bag of words. Bag of words did not capture ordering at all, right? Desert was good is same as good was desert, right? Here everything is fed sequentially left to right. There is a notion of second word, third word, fourth word and so on. So this is a improvement over that.
So when we are trying to generate probably previous slide, so the unit will predict thanks if it is directly. So what if we take long and thanks as the input? Not only the next word, which is actual word, along with that, what if we take the previous predicted word?
Okay, so you're saying rather than and, let's also take and plus one more word which is the predicted word.
No, you said that so predicted thanks. So
Okay, let's say by mistake it predicted thanks, yes.
so I take this thanks
Hmm.
along with long
Along with long, yes.
to the second unit.
Okay.
So now my embedding will have both the actual word and the
Misclassified word, yes.
classified word. What will happen then?
So one thing is that when you are initially training, You typically don't do that because these are very arbitrary. The model is not yet trained properly. So you will give the correct answers all the time. But let's say you've trained it to some degree and now the model is at least right 75% of the times. So in the 1/4 cases when the model still gives a wrong answer and you still input thanks, the expectation does not change. You still want the model to predict and, correct? So because you don't know what would have come next because somebody did not write so thanks something something. What you saw in your data is so long and. So you will continue imagining or assuming as if the answer was right. Okay. So, okay, this is good. So there are a few other interesting things you can do with RNNs. One thing is like, as I was suggesting that we can stack up layers in feed-forward networks, nobody is stopping you to add more layers on an RNN. So in an RNN2, you can have multiple layers where, let's say, the H1 here is the input to the first RNN in layer 2. Similarly, the output here is the input to the first RNN in third layer. Why are adding more layers important? Why were adding more layers in a feed-forward network important? Yeah, great. So they can capture more abstract, higher level features rather than superficial, surfacial features. So the same intuition, same logic, same observation applies here. This is also a way to add more capacity to a model, add more free parameters, so that if your task is more complicated, those functions can also be learned.
What do we mean by that RNN RT?
So basically, like this RNN has a W and a U, right, which is common for this. But the second RNN will have a different W and a different U, which will be common across the second layer of RNN. Similarly, the third RNN layer will have a different W and a different U. So it is like saying that whatever output came of the second RNN is my input to a new RNN.
We will have 3 edge generating from.
Correct. So you will have an edge generating from here and another edge here. Yeah. So like maybe the simplest answer is we don't need to think about it because Autodiff will do it for us, PyTorch will do it for us. But if you really want to think about it, like Y2 is a combination of this H, right, which is a combination of this, and so basically all the weights associated with these affect Y2. So a loss that is incurred due to a misclassification at Y2 will update all these parameters.
From the block at the X1, so are the horizontal and vertical edges same or they are different?
They're different. So horizontal edges are also different because time steps are different. So if you insert third word, your H3 will be different because it now has seen the third word, right? Like think of just one layer neural network, your edge changes with time. Similarly, because the input to the second layer is outputs from the first layer, your edge will by default differ, right? Because you are seeing a different input. So all edges are different, both horizontally and vertically. Yeah. So this is maybe clear. RNNs can be stacked. Another interesting thing you can do is RNNs can be bidirectional. So even though we write left to right, some scripts are right to left, but there might be some signal that is important to capture from write tokens, right? So if you are, let's say, doing sequence tagging or labeling as it is called, where you have the entire sequence with you and you want to tell, let's say, the part of speech tag of every word, whether it's noun, verb, determiner, modifier, you have the entire sequence with you. in some of those applications, people have seen that it is helpful to run a forward RNN which moves left to right and a backward RNN which moves right to left. So how should you think about right to left RNNs? So think of it as a left to right RNNs operating on the reversed string, right? So like the first input to that RNN is the last word, second input to that RNN is the second last word. One second. And once you have two RNNs, the outputs at each time step can be combined. So let's say the output of the forward RNN after consuming x1 is hf of 1, whereas the output of the backward RNN after consuming everything, because this is the first word of the sequence, which means the last word of the bidirectional sequence, will be concatenated with h of backward n. And this could be like your output from a forward RNN and a backward RNN. If you want, you can stack multiple forward and backward RNNs also, right? So if you want to, let's say, do text classification here, right? If you want to do text classification here, it might help to have a context that is captured from right to left. Sometimes it's also better. Why? Because the left to right RNN sometimes can lose out information that it saw a long time ago, right? Similarly, the backward RNN can capture information for those things much better, right? Because it has seen those tokens at the last.
Does this completely solve the problem of that?
No, it does not completely solve the problem, but it is like 1 to 2% better than just using a single unidirectional RNN. Yeah. Yes. So bidirection. So the question is, for language modeling, we are not supposed to know the future tokens. Exactly. So bidirectional RNNs cannot be applied to the task of language modeling. It can only work if you have the entire sequence with you. In the task of language modeling, you only have the prefix and you are trying to predict the next word. So bidirectional RNNs cannot be applied to language models or the task of language modeling. Question, yeah. Yeah. So if you say that I'm going to use one RNN on the string that is as is and another RNN on a reverse string and combine the output, you have just invented a bidirectional RNN, right? That's exactly what it is. So basically, like in this case right here, I am only concatenating after the output is generated. So in some sense, bidirectional RNN is quite independent of the forward direction. Sorry, the backward RNN is quite independent of the forward RNN. Only their outputs are combined.
So this can be parallelized.
This can be parallelized, yes.
How does the second RNN get the output? Independently they get the output, or they have the output of the RNN1?
No. So the backward RNN does not have the output of the forward RNN. It is operating in the right to left direction. That's all. So if you look at this figure carefully, the xn goes to the backward RNN, RN2. Nothing from RNN1 goes to that, right? Only the output is clubbed and concatenated, yes. Yeah. So the loss happens, it will flow through both. So whatever, let's say you combined the output and made a prediction, that was a bad prediction, all that will, yes. So both RNNs will be updated due to a loss. Okay, so I think we finished the RNN component, but remember that there are like two major weaknesses. What were they? Sequential and then longer contexts. Okay, so we'll fix that. Like transformers will improve on those capabilities. So let me go back to the transformer section. Okay, so before I introduce transformers, I need to do some groundwork to explain to you what is this attention mechanism. Attention mechanism is at the heart of the transformers architecture. In fact, the paper that introduced transformers is called Attention is All You Need. So we really need to understand attention first before we start talking about transformers. So attention was introduced in 2015 in sequence to sequence tasks, and that motivation is very important. So we will cover a little bit of sequence to sequence tasks first, and there were also a few questions about machine translation. So we will look into some of those examples also, just so that we cover our ground. So sequence, I'm not going to cover LSTMs, at least this part of the course. There are only 5 lectures, I can only cover so much. So sequence to sequence tasks are everywhere. Like translation is one beautiful example. You have a sequence in English, you want to translate it into Hindi. Dialogue generation could be another one. You said something to a bot, the bot says something. So you give in a sequence, the bot gives you another sequence. Summarization could also be thought as a sequence to sequence task. You give a large document, the model gives you a shorter document or a shorter summary, right? So let's look at translation. So how many of you here understand Hindi? Okay, how many of you don't understand Hindi? Okay. Not the written part. So I apologize for your discomfort, but bear with me. These are only very illustrative examples. So let's say you're translating a sentence from a source language, let's say which happens to be in this case Hindi, to a target language which is English here, right? So the sentence says, "Lal shirt tum par bahut achhi lag rahi hai." The red shirt looks great on you, right? And so as you can already see that it is not a one-to-one mapping. Questions there? Okay. So it's not an obvious one-to-one mapping. So the word lal means red in English, but you don't directly start with red. You say the red. Similarly, the word tum in Hindi is coming a lot sooner than the word you in English. In fact, English follows subject, verb, object. Like I picked the ball, right? Hindi follows subject, object, verb. मैंने ball उठाई. So the uthai part, the verb comes much later. So different languages might have different orderings, and so it's quite a challenging task. It's absolutely non-trivial to just look up words in dictionary and do the translation. You'll barely be able to even negotiate with an auto wala here, right? If you did that, I mean, doesn't work. So we really need like complicated models to be able to like do this. So to be able to build machine translation systems, the key idea is that rather than looking at a dictionary or rather than hard coding what words mean, let's try to learn what different words mean based on parallel data, based on like data that is available to you, and looking at statistics and numbers and what co-occurs with what. And ideally you want to model P of y given x. X is, let's say, the Hindi sequence. You want to figure out which English sequence best translates it. We'll come to this notation a little bit more, but I want to show you what parallel data looks like. So again, for people who don't understand Hindi, my apologies. But let's say, okay, for you, maybe this is an exercise. So there is this word red that occurs in every single word here. So I just pulled out some sentences from a parallel corpus. By parallel corpus, I mean the same sentence is written in Hindi, same sentence is written in English. So people who don't understand Hindi, can you guess which word does this correspond to? Second one? Yeah. So this thing, right? So by the way, I mean, like, for you this seems like very, very obvious. If I change this to Chinese, everybody will be just as clueless, right? So you should sympathize with machines here, right? Like, I mean, we are really throwing a really hard task at them. So the same word happens to come many, many different times. So like there is a lot of statistical patterns that are available in a parallel corpus that ideally you can mine. So just by looking at these 5 examples, even if you didn't know Hindi, you could tell that this funny looking word matches to red. Without knowing Hindi, for instance. So there is patterns in the data that can be extracted, and hopefully that's also giving you a realization that data is so important. So if let's say your mother tongue is Manipuri and there is no data about Manipuri, you don't have this parallel data, nobody can do anything to build a translation system, right? I mean, it's a difficult task. It's a lost cause. You really need to get a high quality data, parallel data. In fact, European languages have some of the best translation services. And the reason for that is very funny. Apparently, because of the linguistic diversity, the European Parliament decided to translate every assembly meeting of theirs formally into 22 different official whatever European languages, or how many ever European languages there are. And there is a very famous dataset called Europarl, which drove a lot of machine translation progress. So political discussions were at least helpful somewhere, right? We owe translation services to them. Similarly, French and English is very good thanks to Canadian Parliament. A lot of French speakers in Canada and a lot of discussions in the Parliament get translated into French. And all of that is available. That is also the case in India, although that data is not so easily accessible. So it is like logged in somewhere. Okay. So now maybe some of you are already thinking ahead. We know RNNs, they can consume sentences, they can generate output. Can I use 2 RNNs? One for, let's say, the source language, which is Hindi, and hopefully produce English. So the way, like, let's say this sentence is Mantri ne jhanda lehraya, a minister waved a flag. So can I, like, again hypothetically, let's think magic happens, right? Let's say we throw in this word Mantri to an RNN, we consume this Hindi sentence as a part of the first RNN. Can Hindi sequence be processed? Yes, I mean, it's like any other language. You can have, just like you had an ID for the word great, you can have an ID for the word Mantri in Hindi and have an embedding for it. That embedding can be an input to a Hindi RNN which consumes the Hindi words. And now after you have consumed the Hindi words, let's say this is your final Hindi time step. Now let's say if I was able to give all this context to the first H0 of the English RNN, can I potentially train it to generate English? Assuming I have some supervision, assuming I have parallel data where I have some examples like Hindi to English is given to me, like the parallel data I showed to you, can I train my RNN to do this? This seems like a Herculean task, seems almost magical for it to work. Ilya Sutskever, who's like now maybe very, very well known, he wrote a paper called, like this is called a seek to seek paper. I think has maybe over 100,000 citations at this point of time, but this was like a groundbreaking paper that showed this can be done. You could potentially, with large enough data, some amount of compute, train this. You can train an RNN and produce this. I mean, at this point in 2025, this seems trivial to people who have been around, but this was a big deal and this should amaze you.
And it is able to do translation better than whatever translation systems existed back then. And a lot of those translation systems were very, very sophisticated, very complex. They used to also rely on dictionaries. They also used to rely on a lot of context in very, very sophisticated ways. They were very bulky, very engineered systems. And let's say a system that was engineered for Hindi to English could not work for Hindi to French because it had a lot of linguistic knowledge. And the teams that maintained translation services were hundreds of engineers. So this is back in 2013, 2014 until this paper came. And this is such a simple idea. You can potentially swap out Hindi to English and bring French to English and do the training again. Same architecture, same idea, same loss function. It just works. Right? I mean, it should surprise you. Even does to me after so long. But yeah, I mean, it's kind of magical. Yeah. Question?
The embeddings in the Hindi,
Yeah.
how is that? Because end of that output I get an embedding.
Yeah.
How that embedding is relevant to the embedding system?
Yeah, great question. So essentially you have a vocab. So the question is about how Hindi vocabulary interrelates or mingles with English vocabulary. So you can think that you have an English vocabulary and an Hindi vocabulary, and your total vocabulary is just like the union of the two. So if you had 50,000 words, let's say 25,000 are for, let's say you have two Shashi Tharoors, like an equal version who speaks good Hindi too, right? Does he speak good Malayalam though? Any Malayalis here? I'm assuming he does probably. But anyway, yeah, so you have basically a much larger set of vocabulary because you are using or relying two languages. So Mantri is another token, so is a minister. They are different. They get different IDs, they get different embeddings. The output here is basically becomes your first hidden state. Okay, and this works to a degree that was comparable to past engineered systems in 2014. So this was a huge, huge deal. This kind of like really gave people a pause that maybe we can eventually have fully neural systems. And this was 2014. Come 2016, every major company had a translation system that was powered by a neural network, powered by RNNs. So because it was so simple to, like so simple in architecture and so simple conceptually, like a few engineers could do it. So since 2016 onwards, no major company has had a translation system that is non-neural. Everything is based out of this or improvements over this. So in machine translation or sequence to sequence parlance, the first part is called an encoder. I'll come to you. First part is called an encoder. The second part is called a decoder. So encoder encodes, decoder decodes. Some people also say that there is a distinction in your mind, in your brain as well. So there are some these weird quirks that have been discovered in people who were, let's say, who had gone through trauma or who might have been accidentally injured, that they might be able to speak perfectly grammatical English, but their understanding component is almost gone. And then there are people who can understand, obey instructions, follow instructions, but the language they speak is quite garbled. So in some sense, like there is an encoder in your brain and a decoder in your brain. There is a comprehension unit and then there is a generation unit. Question?
You said like we have all this actually this is the same RNN and below also is the same RNN.
Yes.
But you said that the sequence generation is difficulty of the RNN, but we are generating the sequence.
So sequence generation was not a difficulty. Capturing long-term context was a difficulty. So generation is okay as long as it does not depend on words that come 10, 12, 15 tokens prior.
According to sequence, like you said one that its sequence is also sequential is also the problem.
So it's sequential in processing. So what that means is before you process ne, you have to have processed mantri. So it operates left to right, it's sequential in nature. That is what I meant. Question, yeah.
So here, for the entire Hindi part, we don't do any back propagation. There is no updating. So the updating only begins when we hit the first English word.
Yeah, great question. So how does updating work? So there's no feedback on Hindi. So only when you start to predict minister and you realize you've done a terrible job at predicting it, you incur a high loss. And this loss goes all the way back and updates everything.
Wouldn't this limit how long the sentence can be translated?
Yes. So this is, as you can imagine, limiting how long a sentence it can translate. It is not very good at very larger sequences. So people were motivated to see this work. So they tried a few other things, which is where attention was introduced, and I'll go into that. So one big bottleneck that you can, okay, let me, before going there, you can imagine that when you are generating English, let's say when you're using this as a translation system, just like a language modeling, if you have produced minister, that becomes your input. If you're produced waved, that becomes your input. So think of this as a conditional language model conditioned on Hindi. Right? So it is, this part is very much like an LM, but conditional. Right? It is conditioned on Hindi context.
I do not understand what is the role of the RNNs from the Hindi text. Because you are
Yeah.
using the text.
So basically RNNs are used as language modeling agents, but at the same time they are also good at capturing features of a sequence, which is why we found that they were useful for, let's say, text classification, right? So the encoder is, you're using RNN as a way to encode your Hindi sequence. So it's a way to featureize your Hindi sequence. Question? Yeah, great question. So encoders are typically bidirectional because you have the entire source sequence with you. So great observation. These are typically bidirectional. Yes.
How much of the performance of this, let's say, typical sequence-to-sequence model depends on the data set? For example, if I substitute the English language with some morphologically rich, such as Bengali or something,
Yeah.
will we get the same performance?
Yeah. So great question. So how much of it is dependent on the question is how much of the performance is dependent on the data set and the languages particularly used. So the answer is, it is quite like there's a complicated relationship, and so some languages, like let's say English and French, they even share the script, right? So Barack Obama might be written exactly like the same way as is written in French as is written in English. So naturally you need less data for languages that are using the same script. Similarly, if you're doing English to Hindi, you need slightly more data because Barack is written differently in a different script. Languages like Bengali, Turkish, which are morphologically rich, require more data because there are lots of inflections that you can have for every word. So I mean it very precariously depends on the data. Like saying that it's independent is not right. Yeah. Keeping the model same. But you can, like with more data, you can keep the model same and still train a model. It will produce an output. There was a question there.
Encoder, you still will try to make it predict the second name.
Okay.
And then if it doesn't produce name, you still have a last function. Go back, make it produce name.
Yeah.
Or does it read on the
So great question. So doesn't RNN also do some predictions here? The answer is no. RNN is just a consumer. The first part of the Hindi encoder RNN is just a consumer of, it just consumes tokens, captures the relevant context and passes on to the decoder. All its outputs are thrown away, like nothing is done with them.
Continuation question, like can we first train the Hindi RNN for language generation for Hindi?
Yeah.
Then that can be used as an encoder. It will help to encode much better.
Yeah. So great question. So the question is like, let's separate out encoder and decoder for once, train the encoder separately on the language modeling task, and then freeze this or start from there and then attach a decoder to that. That was actually quite prevalent. People used to do that. It's a good idea. If you have a large enough data set and an architecture that is good, you may not need it. Yeah, but that's a very excellent idea. Yeah.
Given that most of the languages have the translation services to English, suppose say you have language 1 and then English, and from there to language 2. So if you have 3 such one encoder and 2 decoders, was that used anywhere?
So people sometimes use bridge languages, like to be able to, let's say if you have a system that Hindi can be translated to English and English can be translated to, let's say, Cyrillic. Hindi to Kannada via English. Yeah, I mean, if those two pieces, you have independent data and you are confident, then you can do it, yes. But these days people typically look at pairs and just do like Bengali to French will happen directly without English if you have parallel data for it. Yeah.
A follow-up question. If by a bridge, if we go English, Hindi to Kannada, English back, Hindi to English to Kannada, so there will be a information loss in the translation. So it is just suggested that you should go English, Hindi to that Kannada without going via. So we can just train a model that English to any Kannada, Malayalam, Bengali, and get a first language, Hindi, French, anything. Just train it to English, and English will translate to another. So will be there any information loss between the translation?
So that's a great question. So the question is like, if we use a bridge language like English, will there be a loss in translation? So it can happen. There are definitely some very, very specific words which may not have an analogous English word. Some emotion, some color, some tradition, which may not have the direct mapping. So in that case, you have to work with whatever is the next approximate word that explains that. Yeah.
Have there been any efforts to translate a given language to some shared space and from that shared space to any given language?
Yeah. So those are interesting questions. I mean, they are active areas of research. Some people are actively pursuing that, but none of those are like mainstream. Those are like research toys. Like people work on them. That's an aspiration, but yeah, that's not like deployable.
Suppose we are translating it from languages and they are very similar. Suppose US English and UK English. Then like there is about color, COL1,
Yeah.
COL1. Will they have same ID?
No. So if you are like the ID is dependent on the spelling essentially, right? I mean, if it's a different spelling, you will get a different ID.
But then with the embeddings, because
So
the way it is written with this.
yeah. So okay, the question. So this is also related to the question that, let's say, will this embedding be similar to, let's say, whatever minister embedding we get here that we are using, right? So the answer is, if it is beneficial for optimization, yes. Otherwise, no. So if it helps the neural network do the task accurately, then the embeddings will become simpler, will become similar. Otherwise, no. Okay. So one big issue here is that everything has to come through this guy, right? This is the bottleneck. This is the only point of contact between an encoder and a decoder, and if the information is not adequately captured, or if this does not have adequate capacity, then information about Hindi will never be translated to English or will never be conveyed to the English decoder. So this bottleneck is what attention fixes. This is the problem that attention solves. So let me explain what attention is, and I'll come back to how attention solves this problem. So when you're thinking of attentions, just to develop some intuition, think of them as dictionaries with a key value pair. So let's say these are all the keys. These are all the values. So I'm sure you might have come across hash tables or dictionaries in Python. So this is exactly that. So there's a name, and the name is the key, and the value is, let's say, the office number where these people are. Okay. And now you want to know where is Kinshuk, right? So let's say your query is Kinshuk. So what you will do in a dictionary is go and see, look up this item matches directly. So you will say Kinshuk is in 419, right? So this is what we all know as a hash table or a dictionary in Python. People are already, I believe, comfortable with this. So it takes this notion of a lookup, but in a softer way. So if I'm doing attention, let's say there is Manish. Manish does not actually match with anybody. So rather than saying, okay, I am not going to return anything, it is a soft lookup. It says, okay, maybe the match between Manish and Danish is quite high. Maybe someone actually was looking for me but did not remember exactly. So let's say the match is 0.88, but doesn't look like Yash, so I will say 0.1. Kinshuk, no way, 0.02, and so on. So it will softly match with everybody. Rather than being a perfect match of, let's say, Kinshuk, yes, found Kinshuk, Manish is a better match with Danish than, let's say, other words. So this match between query and keys will give you a similarity, and based on that, let's say the similarity is, let's say, a dot product between these two values or these two representations, or let's say whatever number. So whatever number that you have here, you will output the, let's say the room was V1, V2, V3, V4 to V6. Based on the similarity, you will say that Manish is in 0.88 of V1 plus 0.1 of V2 plus 0.02 of V3 and so on. I mean, if you are doing this for room numbers, this sounds like a absolutely nuts idea, right? Like nobody is in an imaginary room of 411.9, right? And this doesn't make sense. But this is exactly the idea behind a soft lookup. So rather than relying on a perfect match, you rely on a similarity. If the similarity is good enough, then you weigh the output in that proportion. So if Danish and Manish match more often, this value will have a more influence on the output. So you will not say Manish is not found, you will give some value based on how well it matches with the keys, and in that proportion you will weight the values. Okay? Yeah, so that will become very clear when we go back to the machine translation, but right now think maybe match in terms of edit distance. Manish and Danish have an edit distance of 1, so that is a good match, let's say. Whatever, yeah. So this match we will define in some detail. So let's look at what happens. So let's say you have a sentence like Mantri ne jhanda lehraya. Think of this as the hidden states that you have produced at, let's say, time step H0, H1 and so on. So this one knows about the fact that I've consumed Mantri. The second one knows about the fact that I've consumed Ne and so on, right? So now let's say this is the decoder RNN. Okay. Let's assume that it has already predicted minister, and I'm showing you how it works in the middle, and then I'll show you how it works from start to finish. But think that we are somewhere in the middle and we want to produce the next token after we have produced minister. So for a minute, forget about how we produced minister. So now this particular query, which is the hidden state after the English minister, will be your query. You want to figure out which hidden outputs does it most closely match with, And since these are vectors, your match could be like a dot product, right? Because these are vectors. And based on, let's say, the match with this and this, you will have a score. Let's say that score is minus 0.1. Similarly, you will match this vector with the vector after ne. Let's say the match is minus 0.1 and so on, right? So now you got some matches by comparing this query with all the key vectors from the encoder. Now these are not normalized values, so you pull out the favorite trick that you know, you convert that into a softmax, you use a softmax and convert that into a probability distribution, and what you get is a normalized score that sums to 1. These scores are, this is called your attention vector. If the model is properly trained, it will tell you that after I've consumed minister, what in my input should I look at? What should I attend? So this value after training, let's say, happens to be high, which means that I should focus more on this, because I want to predict the next word waved, which is similar to leheraya. Right? So now I have these attention vectors. What I will do is I will consider the same vectors as values and do a weighted sum. Weighted sum in exactly the same proportions. So this leheraya had a higher score, so I will pay more attention to the hidden vector of this. And I will do a weighted average to give me this final output, which will then be consumed by the decoder to predict the next word. Okay? So rather than me just having one signal from the last state of the encoder, I am dynamically choosing which words to look at or which words to attend based on where I am currently in the decoding stage. So that is a broad idea of attention. So let's go back to the sequence to sequence model. So when you have this particular prediction that's already made, you will attend to all of these and you will realize that the highest similarity is to this guy. So instead of this signal that we were using last time, you will do a weighted combination of all these four, where a higher weight is here because of this 0.76, right? And now this will be your context to make the next prediction. So in some sense, from having to rely on just the last output, I have developed an attention mechanism where I can dynamically move to different tokens and attend to them based on where I am in, like which stage of decoding I am.
Is the query same as the word predicted by the RNN, or is it something else? The query vector.
Yeah, great question. So the query vector is the hidden state of the decoder before predicting the word that you want. So if you want to predict the tth word, then the query is ht minus 1.
So the last hidden state always have the information about is always influenced by the previous hidden states at the previous time steps, right?
Yeah.
So if I take a word from here and if I try to do a dot product between all of these, there will be always a good score of this particular vector with the last hidden state because it contains the information from the previous one.
So when you are training a neural network in a way that the only connection between encoder and decoder was through the last stage, then that was your only route to get English outputs. So RNNs were capturing or were at least trying to capture all that information. Now you have broken that linkage. So now there is no incentive to do that. Even though, of course, the model will have more influence from the previous state, but it is not like now that duty is kind of taken away from the last state, right? Because you're not using it until and unless it is matched with that.
We have this because this is an RNN, so at different time step we will have different output.
Yes.
So how that different output we are taking the attention of that like that.
So you will do the same operation after waved. After so this attention operation of looking at different words will happen for every word that you are predicting.
But we have provided this word sequentially to the encoder.
Yes. So attention does not apply to the encoder. It only, encoder does not produce any output. It is just a means of representing the input, right? The Hindi input.
What does that RNN over here represent? Is it just the embedding of?
So to give you one example here, RNN, like let's say the representation. So here, right? So this RNN output here, let's say here, let me maybe draw with blue. This RNN at least knows that the word we are talking about is Lehraya, and Lehraya, what is Lehraya? Jhanda, we have waved a flag. So this has information of that because of an RNN. Because of this context capturing capability of an RNN, only then do we know that, the waving, the subject of waving is a flag, right?
In that case, what is the then difference between having a RNN over or having some kind of embedding layer which captures the context of the word?
Yeah, so for instance, like if this word was, let's say, apple, the word itself is not clearly telling me whether it is fruit or company, but the context might be. So the RNN is useful in capturing that context. So I might be able to translate it into, let's say, Seb or the company apple, right? So which would be for English to Hindi, but that was just an example.
And then what does embedding, like embedding doesn't capture the context?
So the embedding, if you're just looking at like embedding of what? Embedding of Hindi words?
Embedding layer we have usually.
Yeah. So embedding layer will not capture context because that is just the lookup. That is just the starting point. RNN hidden states, RNN outputs will capture some context.
So when it comes to loss calculation, when you are predicting that it should be minister or it should be wave, you don't know the knowledge about what happened in the attention word, right? Whether it attended to the second word mode, third word mode, all that. You only know that it should have been waved, but it is not waved.
Yes.
So how would you propagate?
Yeah. So that's a great question. So how, like let's say I made a mistake, the signal I'm getting is only that I made a mistake. I don't know what word should I paid attention to get it right. But this is where parallel data comes into account. So if the model learns that the query before the word waved is similar to the word lehraya, then that becomes very easy to predict. So it is by virtue of optimization that these things align the way they do.
What will you correct basically? Do you only correct, so because you have to do grading descent,
Yeah.
only do grading descent on the decoder, right?
And encoder also.
So you go all the way.
All the way, yes.
Which will next time change the attention for the next one.
Yes. Attention will, like initially attention will be random because everything is random. Dot products are random. Queries are random. Values are random. But because of the optimization, they will start to take some meaningful values. Where if it so happens that let's say the two things should have a high attention, they did not. It is harder for it to optimize. Like it becomes an easier optimization task if they happen to be similar, and the model then nudges them to be similar.
So you have to train both
Both together, yes. So you cannot freeze the encoder and do it. Yeah, like generally encoder and decoder are both trained together.
Instead of gender, suppose any Tiranga.
Yeah, yeah,
So value also changes.
yeah,
That time also predict the flag.
yeah. No, so Tiranga and Jhanda are different words according to the model. So unless and until the model has seen enough of them in similar contexts, it might not be able to have a similar representation for them. So it might not automatically happen. Yeah.
Tiranga may correspond to tricolor.
Yeah, it might also mean a slightly different word. Like a tricolor might be slightly different translation. Yes. Yeah.
Question, for example, here minister waved the flag, but it can also be flag was waved by.
Yeah, yeah, yeah. So
How does it like?
So how does the model decide which one to pick? So when you're training, you decide based on which one was given to you in the data. So let's say European Parliament, there were these translators who were actually translating. They made that choice for you essentially. In the data that they transcribed, they decided whether to write active voice or passive voice, and now you're just making the model copy that or mimic that. Yeah, yeah. So if you happen to pick a translator who was a fan of passive voice, your model will be a fan of passive voice, right? It's mimicking the data.
Meaning the accuracy will dependent upon the data set.
Yeah, yeah. Accuracy will depend on the training data, and your evaluation will also depend on the data that you are matching with.
So same thing with Chanda, we could have used Tiranga. So let's say we had enough data that Chanda came for a flag, and similarly Tiranga came for a flag.
Yeah.
But for now, for this sentence, like minister waved a flag, how will it be excited to use Chanda or Tiranga?
Yeah, yeah, yeah. So multiple things could happen. One is the model could have a high probability for both the words. So similar words can have similarly high probabilities, like it might be 0.3, 0.4. So depending upon your decoding algorithm, you might generate Tiranga or Jhanda. Or it could happen that the model like has seen one more often than the other, then might prefer that. But it is just an artifact of like largely the frequency in which that instance has been observed. Yeah.
While translating from English to Hindi, while training the model, we have read the word apple as a fruit. But in the context, word apple is as a company.
Yeah, yeah.
While translating, it will translate the word apple into fruit or.
Yeah, yeah, yeah. So these things happen a lot, right? Like if like 5 years ago you said it's raining cats and dogs, it will say kutte, billi, barish ho rahi hai, something like that, right? Which makes no sense, right? So I mean, these things happen. Models will not be able to figure out that you used apple in one context, but magically you are talking about a different apple now. Yeah.
Can there be situation like how does it work? Basically, when there are say different number of words in the original sentence, while
Yeah.
the translated sentence there are say
More or less words, yeah, yeah.
How does it?
So basically, it has to predict this token called stop token or end of sequence token. So when you are training your encoder decoder, you also teach the model to stop. You teach the model to stop at the right point. So the model during generation, if it predicts end of sequence, then you stop generation. Or if it never predicts, you have a higher size like 32 or 100 and whatever, like 128, where you will say, I will not generate more than that because I don't think people are going to try for such longer sentences. So either it's hard coded or it is dependent on the output being the stop sequence. So basically, like long story short, you teach the model to stop. Yeah. Okay. So if you were to, let's say, just train an English, so this is a paper from 2015 which introduced attention. So this map is coming directly from that paper. So what they did was they trained a English to French system. And this map shows that, let's say, when they were planning to predict zone. So for predicting zone, which all tokens were paid attention to, right? So if you look at this line, right, economic, but area was paid more attention to. Like, so zone is similar to area. Similarly, when you say economic, the economic one was paid a lot more attention to. Right? Again, like answering Vishal's question, like this magically happens. Right? I mean, the model learns that it is better for the optimization to attend to this economic because that vector has the most information to correctly answer this, or to correctly classify and get this token correctly outputted. Similarly, like the numbers are obvious, right? Like you will want to copy the number as is. Yeah, so like some languages don't have, right? Like for instance, we said the red shirt looks good on you. There is nothing corresponding to the in Hindi. So sometimes like, yeah, you get nothing.
What will happen when those words don't have any words?
Yeah, so either the attention will be quite kind of uniform or might attend to the last word, things like that. So, okay, great question. So it's not like, so something to think about. It's not a machine that is doing word to word or some sort of substitution. It is like a language model producing fluent language at the end of the day. So when you say the boy or like the boy went to the next place, the next word will very likely be an because of the fact that you are also producing language. So there are two components of it, right? Like there are two, I think, objectives that you are essentially trying to optimize. One is like you want to produce the language of English, and at the same time you want to condition it and have the same output as was said to you in Hindi. So you don't want to compromise either, right? You want to, like, you will get no points for saying the same words but being grammatically incorrect, because you have to match, in your loss you have to match word to word. Okay, so is this clear? So there are lots of ways to compute attention. The simplest one is you just take a dot product of the query value and the key value. But there are some other versions also. There's like a cottage industry of attention mechanisms. This one happens to be quite regularly used. It's just a slightly scaled version so that the dot products don't become too high. Right? So there are two issues with recurrence that remain. It's sequential. You cannot parallelize it. You have to process the outputs before that. And it cannot capture long context. Like if you say the students who were partying hard and were out the entire night are late for their homework, this there actually corresponds to student, but there is just too much in the middle that you forget who is this for. So these are the two problems where we will talk about and like get an architecture solely based on transformers. So we have two choices now. Either we break here, start from this point and cover transformers, or I can take maybe 15 to 20 more minutes, give you an overview of transformers now, and we start from there. So how many of you think we break now? Okay, perfect. So we have quite a consensus. I'm assuming people are not abstaining from voting. Okay, so there is a mechanism where there is an architecture built purely on self-attention. So let's look at this sentence. Students who are late for their, like, let's say who were partying hard in the night and were out throughout the day, are late for their homework. Now I want to, like, for instance, I don't even know whose homework are we talking about, or who are they here, right? Who's there? What does this correspond to? So to be able to do this, there's this new architecture called transformers. Instead of having one embedding for a word, it has 3 embeddings. So it has a query, it has a key, and it has a value. So every word like homework will have a query, value, and a key. So this query will tell me, so this query will go match with other keys. Let's say this query matched very highly with the word students. It will tell me that to represent homeworks, I should attend to students. So just like we talked about decoder attending to encoder states, we are talking about each word in the sequence attending to other words in the sequence. So this is English only, let's say. Forget translation, we are back to one sequence tasks. Here, rather than going left to right in a sequential fashion, everybody can attend to everyone else. Every word can look at every other word. How much should the other word look at the other word? Depends on how well is its query matching with other person's key. So there will be an attention from the word homework to all other words, including the word itself, which is dependent on query, or rather let me just say proportional to query of homework and the key of whatever word that we are looking at. I'll take questions. Give me some time. Right? So, okay. So the query of the word homework will tell me what should be my attention to all other words. And ultimately, let's say this is the attention of homework to word 1. This is the attention of homework to word 2. This is, let's say, the attention of homework to word 7, and so on. Ultimately, my output of homework will be alpha homework 1 times V of the first word plus alpha homework 2 times value of the second word, and so on. Alpha homework of the last word, which is homework itself, to the value of homework. So attention had a few components. Query gets matched to the key. It gives you a similarity which you normalize and take a softmax. That gives you the attention scores. Same thing here, but here the attention is happening within the sentence. Everybody is looking at each other. There is no notion of sequentiality here. Yeah, so generally it tends to happen that words are narcissistic, so they will attend highly to themselves, but very often they will also attend to other words. We'll discuss this a bit more. Yeah. Okay, great question. So what is the difference between the word attention and self-attention? So the word self-attention is used here because instead of a decoder sentence attending to an encoder sentence, the sentence is attending to its own constituents. So words in the sentence are attending to the same words in the same sentence. So everyone is attending to words in that very sentence, including itself. So it's called self-attention. Yeah, you have to give sentence as an input, otherwise there is nothing to attend to except itself. So, okay, great. What do we mean by key over here? So this is a new trainable vector like an embedding vector that we had. Similarly, V is another trainable embedding like vector. So these are new vectors which are random to begin with, but will take differentiated roles. So key will mean something after training, otherwise it's random to start with.
All these keys are actually, all these Ks are same.
No. Actually, that's a good question. So this is K1, K2, K, let's say 7, and so on. So these are all different keys, different values. Every word will have a key query value. So I'm sure you have seen this, right? Like how engineers see themselves, how their mothers see themselves, how engineers' mothers see them. Like there used to be these memes. Maybe this is like a very millennial thing, but something like that. You have a key which tells you how should others look at you. You have a query which is this judgmental vector which looks at other things, and value is what you maybe stand for, which ultimately factors in, right? So I will make this very, very mathematical. You will, I think, it will become very clear, but I'm just trying to share some intuition here.
Basically, this is the same representation of the attention where you had a kind of a dictionary.
Yeah. So this is the same thing. Yeah, this is a soft lookup essentially.
Summation of all alpha HW equal to 1.
Yeah. So we will. So these are normalized. Yes, the softmax operation happens before.
So isn't alpha HW n equal to 1 and all other are equal to 0?
No, because query and key may not be the same for a word, right? Okay. Okay. So let me maybe make this a bit more mathematical. So let W1 to Wn be a sequence. So think W1 being like, let's say 10, 19, 44, 111. Let's say these are 4 words. The desert was good. Okay. So these are indexes. What you do, you pick out a row from that embedding matrix. So now you have 4 embedding vectors, xi's. X1 is the embedding for the, X2 is the embedding for desert, and similarly X4 is the embedding for the word good. Okay. So X is the embedding. Now you have 3 matrices Q, K, V. These are all of dimension D cross D. D is the dimension of your embedding vector, right? Now what you do is you multiply the Q with Xi. What does this do? So your Q is a D cross D matrix, square matrix, and you multiply a vector, right? This way, you know this drill, right? Now basically for every unique Xi, you are getting a unique Qi. So if your Xi is unique, your Qi is unique. 2 different Xi's will get 2 different Qi's. Similarly, for each Xi, you have a key matrix, which is also D cross D. Basically, it's a way to convert one embedding into 3 other embeddings by multiplying with the key matrix, query matrix, and a value matrix. So Vi is the matrix V times Xi. Xi is a vector, V is a D cross D matrix, and Vi is the vector.
What are the initial values of
All random will be trained.
then where are we using the E at all?
E is used to get me an Xi.
These 2 V's are different.
Which V's? So yes. So this is the vocabulary size, sorry. This is the value matrix. Yeah. So I'll change that. Good point, yeah.
But actually, in the previous suggestion, we predicted that V. Here, we are again putting a random value.
So we were not predicting a V. We were matching that, yeah. So what will happen after this, I will show it to you. But at least this is clear, right? I'm using an embedding and I'm getting a key query value. Now, for every word like I, let's say I is homework. For every word I take its query and multiply with all other keys. I do a dot product. So Eij is unnormalized attention I gives to j. Alpha ij is just the softmax of that, right? Exponentiating and dividing. So alpha ij is attention I to j. Okay. So this, how many values will I have here? If there are n words, n square. So every word will attend to every other word, so I will have n square values. Yes. So for every I, all the attention going or originating from I will sum to 1 because of this normalization. No. This is just a vector. This is another vector. This is just a dot product, a similarity term. Yes. Correct. Yes. Every other keyword, not 9 words, 10 words, including itself. Yeah. Yes. Yes. So if there are 10 words, you will have E1 to 10, right? E11, E110, right? Similarly, you will have E51 to E510, E101 to E1010. So you will have a 10 cross 10 attention matrix, which will tell you which word attends to which other word by what intensity.
So 1, 2 and 2, 1 will be same, right?
No, 1, 2 and 2, 1 will not be same, because that depends on keys of 1 and query of 2. 1, 2 depends on query of 1 and key of 2. 2, 1 depends on query of 2 and key of 1.
And this transpose is just for making multiplication possible, or are there?
So this transpose,
Yeah.
this is just notation. These are just two vectors. You can just it is written already, right? Qi, Ki. Like you mean you're the direct? We will get there. Hold on. Yeah.
So we have done this softmax for only for this reason that we are converting into probability.
Yeah.
Differentiability.
No, differentiability is not so much of a reason why we don't want these values to be arbitrarily low or high. We just want to normalize. That's the reason. Yeah. Even without the even without the softmax, this was differentiable.
So why not any other kind of like max min?
Yeah, okay, so why not, so why use this normalization? That has a lot of other useful properties. We didn't really discuss in detail like why softmax over other. So same reasons apply, like softmax is by default the normalization of choice.
What if there's a very long sequence and then the alpha values are like very diffused, so there's not much attention to the...
So for long sequences, ideally if you have trained the model for lots of tokens, it will learn which words are important to it, even if they're far away. Okay?
It will not depend on the total length of whatever may be total strength is.
Yeah. So this is like this, we have killed recurrence, right? There is no recurrence here, right? Every word can attend to every other word regardless of where it is.
But then how do we know that this word comes after this?
Yeah, great question. So how do we know position information? We'll fix that. Hold on. So right now this is positional order agnostic. So then the outputs will be weighted sum of the attention scores, right? This is the same as encoder decoder, same as machine translation. This is the same formula that I had written here, right below. So this is where values come in. This is the only point where values come in. After you've decided alpha ij vj, after you've decided alpha ij and normalized them, you multiply that with vj. Yeah. So this is like saying homework. Let's say if I is homework, then alpha of homework will, let's say the third word is student. It will be 3 equal to student, right? So based on how much should you attend student, it will take that much weighted sum. So if this value is 0.76, then it means the output of homework should have a high component of student.
The previous table you had given that value thing. You have said that that is a room number. So, but here actually multiplying by what exactly?
So here values is also a free parameter. It's a matrix to begin with. So here, like we had introduced this values, it's a D cross D matrix. So what about homework? So basically this tells me that students should look at the embedding of the homework. But what about the homework should be conveyed forward is loaded in V of student. V of student, yes. So if it is paying 0.76 attention, so you should do 0.76 times V of student. We'll quickly go over this next time also, but like I hope you're getting the feel for it.
Sir, in that case, since the matrices Q, K and B are trained over the entire data set,
Yes.
homework will always very strongly get associated with students.
Yes.
If there is a different sentence where someone
So okay, so if it's trained on a large amount of data where this is the case, so the query of student will match with the key of homework. But in some contexts, let's say query of students might also match with the word class. So if there are competing matches, then softmax will take care. Question?
So why we have taken this query key value architecture here?
So why we have done like what do you mean, like are you suggesting that we get rid of something?
I mean, are there other ways also possible, and out of them this was performing best query key?
So I think like the idea of attention started from the machine translation part where you wanted to selectively attend. There query and value were the same actually. If you carefully look, the same vector was used as query and value. So this is a slight generalization of that. And Vaswani et al. Had this idea that we can do attention, self-attention over the sentence itself. So which was like a very new, interesting idea. And there are reasons why this has caught on. I will explain.
The big Q, big K, big B.
Yeah.
When will they get updated?
Depending upon the task you use these models for. So right now I'm just defining the blueprint of the architecture. I have not said anything about what the architecture will be predicting and where will the loss come from, what will be the task. We will come to that. So typically they will be pre-trained on a language modeling task, and therefore these parameters will be updated. Okay. So one thing that is very, very beautiful about this architecture is that it lends itself to a very neat matrix multiplication form. So this part is just like getting the keys. This part, the QK transpose xt is getting all pairs of, so this, like you can go home and like verify this. So this matrix multiplication, so okay, I need to introduce one last thing. So assume that X is the matrix that concatenates all the embeddings, the input vectors, and then xk becomes all the keys, xq becomes all the queries, xv becomes all the values. This is just writing it in matrix format. Then this you can go home and verify becomes the attention scores, all pairs of attention scores. So this is a multiplication of again queries with keys. So this is nothing but queries with keys. You can go home and verify this. This is like xq times k transpose x transpose. This is the same formula written in matrix format. Once you have all pairs of attention scores, you can apply a softmax over the entire matrix and then just multiply with the value matrices. So all of this can happen very, very quickly in a GPU because it lends itself very, very beautifully to a simple matrix multiplication formula, which is why it is so easy parallelizable fast on a GPU. I mean, the reason why transformers won and RNNs did not win is partly due to this.
In the previous slide, what was the where were we using the OI actually?
Great question. So OI will be used further in the architecture. So we have started from W1s. We have given you OIs. I will use OIs later for future. Yeah. Yeah.
We were taking that attention, then we are taking that revalue out of that, and then
Yes.
why exactly this X transpose is required?
So okay. So this is basically this formula, right? I think so. You can go home and verify this. Otherwise, if you're finding it hard, we can go over it in the next class. But maybe this is exactly the same formula that I have written down in matrix form, like what was written in a vector form. So this is the like matricized version of this. Yeah. No, X is an N cross D matrix. Yeah. V is a D cross D matrix. So this becomes N cross D. And this is an N cross N matrix. Because there are N words, attention is N cross N. So ultimately this will give you an N cross D output. For every word it will give you a D dimensional O output. I mean, this is not very hard, but might look a little tricky with these obnoxious formulas. But go home and convince yourself that this is the same as the vectorized form. So this is no longer sequential. It can be parallelized. And interactions between two words do not depend on how far they are. Every word attends to every other word. Okay? So we have solved these two problems just by the virtue of defining self-attention. I will start from here next time and show you how you can use this block and compose it into a bigger architecture, but this is like the meat of this. Like the self-attention operation is essentially the meat of transformers. So we will start from here next time. Here we need to know or fix a large enough n, which is why a lot of these models are like, oh, my context size is bigger. That's where the debate is coming from.
They define this length of this context again, right? I mean, why, here, because we define every query to every query. So, but this should not give me a problem of context. What people also, like what I suppose they say, I have to get to why
So we'll discuss that next time. I'll go over this in more detail.
So if you take all these alphas and basically order it like along ice.
Alphas along?
Alphas along ice only.
Along
Along
ice, okay.
So you take
Sure.
because we are taking
We can end this. Yeah.
we were actually taking I for
Yeah, got it.
so if I take I and plot this alpha images,
Yeah.
so how will it look like?
I'll show you some visualizations next time. We typically use multiple heads of attention, not just one. Some attention heads will just look at itself. So you will see almost like a diagonal matrix. Some will look at the stop token. Some will look at words right next to it, left to it. Different heads will have different properties.
So why I was asking is like will temporal modeling of those alphas the order will it have any when it gives
Some?
some meaning like if you model it temporally using an RNN we have got all these alphas I feed all these alphas to an RNN and get the context instead of the positional encoding try to do later. So we have a smaller RNN which will take care of the positions and these alphas are taking care of the so that the major complaint that people have is like there is no recurrence in
RNNs in attention. Yeah.
so if you take these alphas and try to model bring in the temporalness and then keep use the same parameters. In fact, you can get both.
So you may be able to get both, but you will definitely lose out on the parallelization bit.
Parallelization in terms of alpha is being done.
Okay.
So I now take these alphas and then try to bring it in the temporalness using these alphas itself.
So either it will happen directly or automatically because of the patterns.